Hey guys, welcome back to 118. Hopefully you got a well-deserved rest over break. I know I definitely did. Welcome to 118B, a class that is considered very, very different daemon than 118A, but it doesn't have to be too bad as the name would suggest. Sometimes this class ends up being a lot better for people. But in any case, let's just get right into it. 118B begins with the study of alkenes. And so it might help us if we're going to study alkenes to kind of remind ourselves about the structure and bonding and all that. So we can look back at that. I think it might help us to actually first look at, you know, a normal alkane bonding structure and then apply what we just learned to, to an alkene. So we can look at ethane, ethane molecule, the simplest bond in organic chemistry. But let's give it a little more flavor. Because that line looks, it looks like a hair on the screen. So let's kind of, add some more character to it, see what's going on here. So one thing you might remember from 118A when we talked about bonding and structure is that a lot of the things that we say about bonding and structure is sort of like justifications for things that we observe. So it's not necessarily that we knew these things and then, we made the rules about them. Really, it was that we kind of observed a bunch of stuff and then we try to explain those observations. For example, one of the things that was observed is the bond angle between all of these single bonds. Maybe that's actually the first thing we should have noticed, actually, is the fact that this is all single bonds. And, the angle on these single bonds is about 109.5 degrees. Okay, that kind of helps us realize that this has to be sort of like a tetrahedral shape. So we know this has to be a tetrahedral. And to kind of help you guys remember what a tetrahedral looks like, the kind of drawing that I like to think of is you can draw a cube. I apologize, I'm not an artist, so this might come out really bad. We could draw a cube here. Okay. Where the center of that cube, you can say, is there. And so if we kind of define these objects here as different groups. Okay, we can put 4 groups in these corners here. I realized I really messed this up here. Again, not an artist, so I apologize. Let me see if I can do this actually. Okay, that's actually a lot better. Okay, down the middle. Then we sort of have bonds, right, to these 4 different things. And so a tetrahedral shape with this 109 degrees kind of maximizes the distance between these 4 objects. So it's okay if this doesn't make sense. I just wanted to offer as a visual, if you needed it, on how to visualize a tetrahedral. But this is a 3D shape, right? I had to use a cube to help visualize this. So it's a 3D shape. And so with this stuff in mind, we can look at the orbitals on carbon. And so a little bit of a reminder, right? What orbitals do we have on carbon? We have the s orbital, which I'll put in red. And then we have 3 p orbitals, which I'll put in blue. Okay. Now, if we were to look at the valency of carbon, carbon has 4 electrons. So 2 in the lower section and 2 up here. You might notice that one of the orbitals on carbon is kind of empty. It's kind of like left over, has nothing there. So it's a little bit weird that carbon can make 4 bonds, yet one of its orbitals is kind of empty. So maybe it's not so possible that we're getting bonding just from a normal s and a normal p orbital on all 4 of the bonds that carbon's making. And so the way that we justify all of these observations is we say that maybe there is some kind of mixing going on. So maybe all these orbitals are mixing to form hybrid orbitals. So red and blue make purple, right? Yeah. So we get these hybrid orbitals here that are in part character with some s character and some p character. And what we get are 4 orbitals with 1 electron each. And all these orbitals need now is another electron to form a bond with something, to be happy as a pair of electrons. So now that we have this, we can kind of redraw our ethane molecule. You can sort of say, okay, we have a p orbital here. Draw one here like that, right? Or sorry, we have the hybrid orbitals, what I meant to say. We have those hybrid orbitals overlapping like that. And when those orbitals overlap, they add together. Okay, so really what they're making is this here. And so it is this area in which the electrons in this bond can sort of hang out and be happy. Okay, carbon also makes, right, 3 more bonds with hydrogen. Hydrogen only has an s orbital, so it doesn't have all the fun, you know, hybridization shenanigans as we see here. So I'll just kind of draw it like that, just for the sake of simplicity and for the sake of just, you know, being able to move on without spending all my time drawing. What we get is sort of this picture here, where carbon has these 4 single bonds, right, to other atoms. And in particular, this single bond we call a sigma bond. Okay, so, you know, a question that I always tend to get is, you know, how in the world did they come up with the term sigma? Sigma bond actually comes from the fact that if I were to draw out what a sigma bond looks like, which looks like this, right, you can actually draw a line down the middle here. And if you were to rotate on this line, you'd notice that the symmetry is always kept, or, you know, you can rotate this and it'll always look the same. That's actually where sigma comes from. Sigma is a symmetry operation. And this is the symmetry operation that it is. If you take like Chem 124, I think that's the inorganic chemistry class, you'll get a lot into this. But yeah, this is where sigma comes from. I like to think of this as like a rotisserie, or I think you can call it a trompo. I think it's called a trompo. I might be wrong though. Anyways, that's where sigma comes from, and that's the name that we give to these bonds that are in the middle. And if we were to draw a line down the middle, we can rotate them and they would be that. Okay, cool. So I'll keep this on the side here for anyone who's interested. I'll keep this up here. But again, right, we mixed 1 s orbital and 3 p orbitals. So what we get out was 4 orbitals in total, because we mixed 4, so we must get 4. And those 4 orbitals are going to be sp3, right? S1, 1s and 3p. So in a sense, it's S1, 3p, but we don't have to say 1. We just say sp3. So we get 4 sp3 orbitals. Okay. These 4 hybrid orbitals make 4 sigma bonds. Okay. From the hybrid orbitals. Okay. And there's one other observation we could make about these bonds, or about this bonding scheme, but it won't make sense until we talk about sp2. Like, I'll just be saying this thing to say it rather than us noticing it. So there is still one more observation we can make, but we're going to hold off on that for a second. Okay. So if we apply the same idea to ethene, which is ethane, but with a double bond again. So what is that going to look like? It's going to look like C double bond to C. Now we have an H here, an H here. Again, we could make some observations, right? We can make the observation that now the angle is 120 degrees. Oh, so that's Celsius, just 120 degrees, which to us tells us it is a trigonal planar shape, right? And so trigonal planar, as it, you know, the name suggests, is planar. It's flat. So it's 2D now. It's no longer a 3D surface. So you can think of literally just flat on the page is good enough to understand what that shape is. Don't need anything complex like a cube to help us figure that out. And so when we look at the orbital makeup, what we have again is going to be an s orbital, which now I'm going to use yellow. So I apologize, that's a little hard to see, but I can't think of any other colors that can mix well with blue and I'd know what it is. And then we get the 3 p orbitals. Okay. Now here's where, you know, I could just tell you the observation. We can kind of extrapolate it too. But again, if we look at the structure, we have 1, 2, 3 single bonds on each carbon. And then we have this interesting double bond thing going on here. If the single bonds were made up of hybrid orbitals, and here 4 hybrid orbitals made up 4 single bonds, then that must mean that if we have 3 single bonds here, we must have 3 hybrid orbitals, right? So only 3 mix this time. Okay. If only 3 are mixing, that would tell us that we have 3 hybrid orbitals with 1 leftover orbital. In this case, that's going to be a p orbital that's left over. We made these 3 hybrid orbitals. Again, I'm not an artist, so I apologize. Once again, we have electrons. one for each orbital. Okay. Keeping in mind that, one question that there might be is, how is it that this orbital got an electron if the electron should have, that one rule, I forgot the name of it, but we should always fill the lower ones. Keep in mind that only 3 of these mix. So we can say these 3 mixed, and maybe this middle one didn't mix. So this middle one always kept its 1 electron, whereas these 3 kind of shared their electrons. So way to think about it. Cool. So we get 3 of these hybrid orbitals. And again, we can sort of redraw now our interpretation of ethene, sorry. Once again, right, we can have the 2 hybrid orbitals in the middle, adding together to make one, large orbital, that sigma bond right there. So we definitely have a sigma bond going on. And definitely sigma bonds to hydrogen as well. Luckily for us, it's a lot less sigma bonds, right? We don't have to keep drawing forever. Hydrogen. But the thing is that, again, carbon likes to have 4 bonds, right? So we can get to the octet. And we still have this leftover p orbital. So when we draw in that leftover p orbital, it's a lot harder to see in this sense. But if I were to draw it in like a more accurate depiction, what's going to happen are these p orbitals are going to stack like this, where the in phases are next to each other, right? You might notice that these can, add together, and so can these. So what's actually going to happen here is we're going to get addition overhead as opposed to on head, and we get a pi cloud. Okay, so once again, this should mostly be review from 118A, hopefully, and if it isn't, that's okay. I'm reminding you things to think about, right? This is what the bonding scheme looks like. Just going to move that over because we need the space. So this guy here is our sigma bond. We have this new overhead overlap, and that is going to be our pi bond. Okay, so that's our double bond hanging out there. That's our pi bond. Okay, pi also has symmetric roots to the name. I honestly don't remember, so I'm not going to try to lie to you as if I know why. Completely forgot what it is, but that's okay. We don't really need to know for inorganic chemists to worry about. So once again, right, we added 3 orbitals together, so we get 3 out. In this case, it's going to be sp2. This case, now we have 3 sigma bonds, right, from those hybrid orbitals. But now we have 1 pi bond, and that 1 pi bond uses our unhybrid p orbital. Okay, so this is what I was mentioning before. If I had mentioned this here, it wouldn't have made sense because there was no pi bond yet, right? So it didn't really make sense to talk about it. But now that we've talked about sp2, it's okay. We can talk about it now. So it tells us that there is no unhybridized orbital here. So a lot of information we can get just out of the bonding scheme there. Okay. Another kind of thing we can think about is the fact that, these electrons here, when orbitals are the same energy, we call them degenerate. Okay. They're degenerate. These degenerate electrons are all about the same energy, and in a sense, they're pretty low energy. Okay, they're somewhere in between S and P, so they're lower energy. But here we have clearly 3 degenerate electrons, but we have 1 electron that's really, really high up. It is not degenerate to these, and it's higher in energy. This electron here, really the pi electron, so the pi bond electron, this guy is going to come in handy when we do reactions because it's high energy systems that are going to be reacting, right? So pi bonds that have higher energy electrons, so we'll say high energy, right? These are the guys that are going to be doing a lot of the movement that we'll see in reaction. So kind of look out for that. Another thing that we can kind of take out of this data that isn't exactly said, but I could say it and it'll make sense, is if we look at the chemical makeup of the hybrid orbitals, we can kind of say that, okay, if S is 1 part to this orbital and P is 3 part, we can kind of say that this orbital is 25% S and 75% P. Okay, let me get rid of this here. We don't need that anymore. Okay, we could also say something similar here, right? In that if this is 1 part S and 2 parts P, that is like 33% S and 63% P. So why is it that I'm making making us look at these numbers and stuff. Well, one thing we can see is that the s character is particularly low in the sp3 orbital, whereas it's pretty high in p character. The opposite can be said about these guys. Well, not necessarily opposite, but relative to each other, right? S is higher in the sp2 series versus the sp3, versus p is lower, right? So there's more s character in sp3, less s character in sp3 than there is in sp2. If we were to just look at an s orbital versus a p orbital, right? Why is it that this kind of matters? Well, look at the distance, right? The perceived distance that an electron could have. So let's say that there's an electron pair all the way at the end of the orbital, right? Look at the distance that those electrons could have. In one case, the electrons are pretty well bound to that nuclei, right? So these electrons here are pretty close. The farthest it can be is not very far. Whereas the electrons in a p orbital, they can be pretty far away, right? They can go all the way out there. So why am I making this big, argument? You can also kind of see it too if we look at, just the unhybridized section. The electrons that would be in an s orbital are lower in energy, versus the electrons in a p orbital are higher in energy. Okay, they're higher in energy. We can also think about this as these are technically more stable electrons, right? These are relatively unstable electrons. I don't want to, I'll probably get rid of this label actually. It's not to say that they're always unstable or always stable, but you can kind of think of it that way, right? That these electrons are more stable than these electrons. If I really wanted to push this, right, like I really have to make a jump here, help you guys make that jump. What I'm really looking at is the fact that electrons that are lower in energy and stable here must suggest that the s orbital is more electronegative than the p orbital, right? Because those electrons, they are bound to the nuclei, or bound closer, tightly to the nuclei. So this orbital must be in some sense more electronegative than this orbital, right? The s orbital and the p versus the p orbital. So if we were to look at sp3 versus sp2, where there is more, less s character in sp3, more in sp2, we can kind of even just focus on just the s part here. sp3 with lower s character must be less electronegative than sp2, which has a higher s character. So this must have more electronegativity associated to it. Okay. So why is it that I'm making this big point about electronegativity? Well, we can kind of think about a couple of structures that we've seen in the past. Namely, what I'm trying to get at initially is if we thought about acidity. Oh, let's use this color actually. Okay, so you might remember that alkanes were considered probably the least acidic thing on the planet. And that is very true, actually. We don't actually make carbanions using bases, and we use metals to make them. Which should remind you, what think about that for a second too. What metals we use to make carbanions? It's a good thing to remember. So we can have this anion, or we can have this anion. So if we just talked about, the fact that sp3 is less electronegative than sp2, think about that. What does that mean about acidity of an sp3 alkane versus an sp2 alkane? Alkene. Which one would be more acidic? So take a second to think about that. Well, if sp2 is more electronegative, that should mean that carb anion is way better on the sp2 center than the sp3 center. So carb anion is going to form very, very fast, or very, not fast, but very well. I guess a good sort of study of this is if you remember the way we made carb anions in this class. You could do MGBR like this. Actually, you listed the 2Li. 2Li is also the same thing, but my example will make more sense if I use Li. But we could do this where we exchange the X for Li. And this is like a sort of organolithium or Grignard that you guys are hopefully very familiar with. So if I were to do the same thing, right? If I were to have, let's say, an alkenyl halide, right? So this is an alkyl halide, this is alkenyl halide, and I were to do the 2Li process, that should mean that this reaction works well too. And actually, this works very, very well. So if this works, this must work, and that is true. Both of these work, actually. This process actually works really, really well. In fact, you can do this by using an alkyl base. So if I actually took this base here, or this carbon anion, right? If I took this carbon anion and I exposed it to this alkenyl halide, you will actually form this product very, very fast. This is known as lithium halogen exchange, where alkyl carbon organolithium, so alkyl organolithiums will switch their carb anion with alkenyl or aryl. So aryl means just, you know, if it's a benzene ring. So let's say I had this instead. If I use that same guy, the Li and the X will switch. It's sort of like an acid-base reaction, except these are way faster than acid-base reactions. You will get this as the byproduct of this reaction. You don't actually need to know this. I just think it's really cool. And it kind of helps exemplify like, oh yeah, that's something we just learned. That's like an, you know, it's immediately proved by this type of reaction. Okay, so carbon anions are very easily and, you know, very well formed on alkenyl centers. So that could beg the question of then, okay, so if carb anions work, what about carbocations? So a good reminder of how carbocations form in this class. So you might remember SN1 type reactions, or SN1E1 type reactions, where we have alkyl halides leaving as such. So then we could ask ourselves, okay, how about then if I had, right, an alkenyl halide leaving, right? What about what this guy leaves and we formed a cation here? Okay, how well would that cation form? And is it better than the sp3 reaction? So take a second to think about this. Maybe even try to use the reasoning you did for here, right? So let me give you a model then. So if the model initially was thinking about, you know, what was electronegative orbital, right? We can do the same thing here. So this is sp3, this is sp2. So originally we thought about, right, if there was electrons here, so that dot counts as electrons, we thought about which orbital was more electronegative for electrons. So now consider if there is a cation here. That's what, this is actually a pretty good starting model you can think of. There's a better way to think of this, but you can think of it as a cation if you'd like, if it helps you. But think about if there was a cation there, right? How would that work? Take a second, think about that. Maybe even pause if you have to. So if we pause and thought about that, the cation model, you know, it's a good thinking model, right? If you just think about, right, the fact that there, you know, the nuclei is a cation. So if the orbital has a cation, right, cations don't like each other. They want to be as far apart as possible, right? So that's one way to think about it if you like. And if you think about it that way, I think it helps you come to the conclusion faster, right? If cations don't like each other, then they want to be far apart. And the larger orbital, right, that allows that, or the less electronegative orbital we have that allows that, right? So sp3 is way better at holding cations than sp2. The more traditional way to think about this problem, though, is to just think about, okay, if I wanted to make a cation from either of these orbitals, right, that must mean that I'm pulling electrons out. This actually, now that I think about it, this might actually be the easier model to think about than the other one. So I apologize if I confuse anyone with that last model. But if you think about it, you're just thinking about, you know, how easy is it to pull out these electrons? So think about it. If something is electronegative, you think it's very easy to take away its electrons? Not at all, right? So the more electronegative orbital is going to put up more of a fight giving up its electrons versus the less electronegative orbital will just give them away very easily. Okay, so carbocations form way more easily on sp3 centers than sp2 centers. And so if we sort of, again, think about our model here, this is probably never going to work, actually. So we're probably never going to see a case where we get, like, for example, this reaction here, a hydrolysis of an alkyl halide. This would probably work, probably take a long time, though. but this here probably won't work. So this would probably never work, actually. This structure here actually is a really special structure. You'll get really, actually, you'll talk about it a little bit at the end of the alkynes chapter. And then you'll talk about it a lot at the end of 118b, but still a good model structure. Like this reaction would never just work in general, but this one would work though. This one would work. So SN1E1 type reactions, probably not going to be the best type of reaction right off the bat for an alkene carbon. Okay, that's not to say that we can't have cations forming from these structures. Probably just not from this, particular pathway. This particular pathway is probably going to be forbidden. Oh, wrong color. Probably going to be forbidden. So then the last thing that we could talk about then is, okay, carb anion, carbocation, kind of understand that. What about radicals? So radicals are also a model we should consider. Oops, that should be a single bond. They should be a double bond. Okay. So radical is also a system that we should consider. And this question is really simple. If you just think about, who is the radical more related to? So more related to the carbocation or the carb anion. This might take a second to think about. Definitely remind yourself if you have to by looking at your notes or something. But if you just know which system it's similar to, then this problem becomes very, very easy and simple to solve. So if you took the time to look, hopefully you did. If not, then go ahead and look now. But radicals are defined as electron deficient centers. So that means that if they're electron deficient, they should be more similar to carbocations than carb anions. And so if carbocations are better on sp3 centers, then that means that sp2 centers kind of lose out. It's definitely going to be better here. Okay, cool. So what is the model for this reaction? Well, you might remember we would quite commonly in 118a, I mean, the first reaction you learned in 118a was actually the Br2HV reaction, which turns a CH into a CBr, right, or a CX. That's probably not going to be possible on ethene. You would need a lot of energy, actually. The nice thing actually is that we can quantify these reactions. A good measure, not an absolute measure, but a good measure you can use is bond association energies. For this reaction here, I would reckon it's about, I don't know, I'm just going to make up a value. If I had to give it a value, I would say 100 kilocals. Let's give it that. I don't really actually know. I'm just making this number up, to be honest. 100 kilocal. Actually, I could put it up here. Let's say this is about 100 kilocal. Then if I had to make a comparison point for this one is probably going to be like 110 kilocal, which that doesn't seem like a big difference, but it's these small differences that actually add up and really, cause differences in reactivity. Now, I also want to make sure what's understood here is that I'm specifically making, right, a alkyl radical versus an alkenyl radical. If I were to react this substrate here, though, so let's say this substrate actually, and I did a Br2HV, I would definitely get a reaction, but it would not be this product, because you might think it's this one because there's an alkyl carbon. It's not going to be this one, and it's definitely, from what we just said, not going to be this one or on this side, right? It's not going to be on either of those sides, so it's not going to be this one either. What's really left over then is that it's going to be this one here. So you can go ahead and think about why that one is the best one. I'll give you a hint, right? If you draw the radical, you'll probably kind of see it. Right, a concept from 118a that I always tell everyone will always sneak up back on you throughout the rest of the course. But there is definitely something special about this radical, and that'll explain to you why this radical here, to form it, is actually a lower energy than both the alkyl and the sp2. To do this one, I would give a value of like 95 kilocal, right? 95 kilocal. Again, I'm just making these up. They're probably really wrong, these values, but just a way to think about them. Cool. All right. So again, I know I threw a bunch of reactions on here. don't be too frightened by them. They're just models, and just ways to think about, how are alkene carbons different from alkyl carbons. Really, the takeaway is that alkenes are more electronegative than alkanes, and that, traditional cation or radical reactions that we did before probably not going to work as well. But organometallics are going to work very, very well, actually super well, considering that our alkyl organometallics will make our alkenyl organometallics very, very easily. So actually, there was something I said there that we should expand on a little bit, right? Alkyls, right, or alkenes are more electronegative than alkanes. So if I take that model molecule from before, this one here, and let's sort of mark the carbons, right? This is our sp3 alkyl carbon. And then this is our sp2, right? These are sp2 alkene carbons. If the alkyl is less electronegative than the alkene, something should be forming across this bond. Maybe a way to help you guys think about it is, if I had, for example, a CCl bond, right? What would form across this bond? Same thing that would form across a COH bond, same thing that would form across a CNH2 bond, right? What is forming across this bond? If these things are differing in electronegativity, right? The electrons on the bonds are a little bit biased, right? They're not going to always hang out equally with both of them. One of these guys is cooler, right? The thing that's forming is going to be a dipole, right? A dipole is forming across these to sort of signify that there is a difference in electronegativity. So if sp3, again, sp3 carbons are less electronegative than sp2 carbons, then that to us means that there should be a weak dipole moment here. Because again, these are still carbons, but there is still a difference, so there can be a weak moment here. Now, this concept actually isn't foreign to us. Hopefully it's not, because we've seen this before, actually. And I'll draw the model for it, and then we'll kind of figure out what it was. But we've seen in the past where sp3 carbons have donated electrons to an sp2 carbon for some particular reason. So what would be here, right, to make this model make sense? What was it that we used to see before? That thing was a carbocation. So hyperconjugative forces are exactly what we used to see in the past. It's what we're seeing going on in the alkene, right, with an alkyl substituent. Another way of thinking about this is that sp3 carbons are donating groups, they're electron donating groups to alkenes. I apologize now for any of you guys that are new. My handwriting is atrocious. So I will do my best to say what I've written down multiple times. But if it's still hard, please let me know, like say something, like write a comment or something. And I'll try to do a better job in the future in regards to my handwriting. Okay, anyways, carbons, right, are electron donating groups, and really by induction. So I should mention here, they're by induction. They're donating via induction to this carbon here. So that's pretty interesting, right? We have hyperconjugative effects showing up in alkenes. And one thing to think about is then, okay, well, if this carbon is donating to this particular carbon of the alkene, not necessarily this carbon, how might the double bond be polarized overall, right? Because sure, right, the electrons are in this pi bond, but are they more biased towards one carbon or the other, right? So if I wanted to draw, let's say, a polarized model, let's say, I move the electrons this way, so we have an anion, cation here, or I move the electrons this way, so that the electrons are here and not over there. Which one do we think is more correct? So definitely take a second to think about this. Maybe think about, hyperconjugative, right? What was the alkyl group donating to? So what might that mean about the carbon here? Which model do you guys think is better, A or B? So take a second to think about that. So hopefully you paused and thought about that. The better model, right? If hyperconjugative forces donate to cation, then that probably means that this carbon here, if it's being donated to, is a cation. So A is the better model here. B is not going to be the model we take on. And this also just makes sense if you just think about charges in general, right? Carbocations like to be on the more subcarbon, and carbanions like to be on the less subcarbon. So it doesn't really make sense that these charges will be opposite. Actually, you can even just, rationalize by saying that this primary cation can never exist, right? So that's another way to think about it. But really, the better reason is that, cations like to be more sub and anions like to be less sub, because cations can be stabilized by neighboring carbons. Okay. I think that there's always this misconception in this class that because this carbon is donated to this carbon, it should be like a delta minus. I've seen that in the past. People have said that before. That doesn't really make sense to me. And hopefully it doesn't make sense to you either. Because, well, why would a carbon that's being donated to electrons, be more willing to carry all those electrons, right? Those electrons want to be diffused and move around. In reality, you can think about it as really this way: is the electrons are, I don't know how that happened. Electrons are really being pushed right around, right? They're being, moved, they're being influenced by this group. And so this general movement, right, where the electrons are pushed through the pi bond or pushed to the other side of the pi bond, is something we tend to see with electron donating groups. Okay, electrons again like to move. And so really we should expect to see sort of a delta positive here, a delta minus here. That's really going to help out because when we do reactions with alkenes, again, polarity is going to really help us determine what parts should go where. For example, right, you don't have to solve this problem now, but you can think about it. Let's say I did a reaction where I had H plus and alcohol, right? Knowing from this class that H plus is an electrophile and that ROH is a nucleophile, maybe you can already guess where things are going to line up and add just by knowing those two things. So already being able to solve our first reaction in this class just by looking at polarity. Now, I don't want you guys to just memorize the fact that this is a polarization that happens. I want you guys to understand it. So I want to offer you guys two models to think about when you think about donation versus the opposite, which is withdrawing that can occur on a pi bond. So let's actually start with a counter example, right? So what is an example where this might not always be true, right? Let's say I have the alkene here, but instead of having a CH3, we have a carbonyl. So this system here is known as an enone. You guys are really, really, really going to get to know this guy at the end of the quarter. Enones are very, very popular and important. You actually kind of see it a little bit of midterm too as well for our very famous Dipolar reaction. So you're going to see it quite a lot. But this alkene here, right, has a differing polarity than we might expect because of this carbonyl group. So definitely, I would say, I'll give you a hint on how to think about it, but definitely look at the resonance forms here. When you're solving this problem, right, solving this enone problem, I would say figure out the polarity you already know because of 118A. 118A told you the polarity of one of these groups, right? What it's always going to be. And then from that, justify what the polarity must be of the pi bond. So definitely pause and take a couple minutes and try to figure that out. So hopefully you tried to figure that out on your own. But again, one of these groups, clearly the carbonyl, is something we already knew, right? We knew from 118A that the oxygen in the carbonyl likes electrons. So one polarity we already know is that the electrons are going to go into the oxygen like that. So that puts a cation on this carbon here. And so if there's a cation here, I mean, there's really two ways to rationalize this one. One way is that if there's a cation here, there's no way that electrons are being donated by the carbonyl into the pi bond. Really, it's the pi bond that's donating into the carbonyl because these are electrons and they want to go towards cations. So we can move electrons here. Oops, sorry, not what I meant to do. And so now what we get is that the terminal carbon of that alkene is going to be cationic, which is a bit different from what we saw earlier, where the terminal carbon was anionic. Okay, so before we saw that there was an anion on this carbon. Now we're seeing that there is a cation. You could also, break up the polarity here too. If you really wanted to, you could move electrons here so that you could see the true polarization of the pi bond, quote unquote. Right, and now you can see that this, this pi bond here has a very clear anion here and cation here. Once again, it is the substituent that directs the effect, right? The substituent determines what should be the polarization of the pi bond. Now, if we did that same reaction, right? So actually, let's go ahead and let's finish this one up, right? If I did, so I know this is positive and this is negative. If I did that H plus ROH where I know that ROH is a nucleophile and H plus is an electrophile. Electrophile is like anion, so H would probably go here, and ROH likes electrophiles, so it would go here. Okay, so we can already solve this problem. We don't have to draw on the H, but I drew it in just so we could see it. But we can already solve where these two components would go just by knowing our polarities. If we try to do the same problem, right, but with the E known, things might be a little different. Where do I do this? Let's do this down here, right? Because now I have an anion here and a cation here. So when I do that H plus ROH, right, things are not going to line up exactly the same. So where would things line up, right? Where would ROH go and where would H plus go? If we follow the same rules as here, OR should go where the cation is and H should go where the anion is. And that's exactly what we see with this kind of problem. Okay, just focus on the pi bond. I know that there's also a cation here. I'm aware of that, but let's only focus on the pi bond for now. This is a valid answer, and it's an answer that you'll be writing in your exams at the end of the quarter. So already, just knowing polarities, we can solve problems. Knowing polarities will help you solve many, many problems. Okay, and we see that here. And again, directing effect of the carbonyl on the pi bond tells us how things should react. Okay, so resonance effect, and this here is electron donating group, electron withdrawing group. There's actually, you can shorthand this, so this can be shorthanded as EDG. This here can be shorthanded as EWG because it's withdrawing. It's just withdrawing via resonance. Okay, via resonance is where the withdrawal is happening. It's happening. Okay, cool. So actually, I'll keep this up. I'll just move this over to the side. So then, what's an example of a resonance, EDG? A great example is the enol ether. So this is known as an enol ether. And once again, enol is something we will come to understand at the end of the quarter. Although this particular structure, you'll probably never come to understand. It's just okay. It's okay though, no big deal. Once again, we can think about how resonance plays an effect here. So go ahead and try this one out. Very, very simple if you apply the same logic we did here. Just think about, right, if we have a pi bond and a heteroatom located next to it, how is that heteroatom going to interact with the pi bond? So take a second to think about that. So hopefully you paused and tried. This should not be too bad, not should be too hard. Right, heteroatoms adjacent to pi bonds tend to donate their lone pair in as long as they have one. Oxygen is a very good pi resonator. And what we get here is this resonance form here. So we get sort of a congruent answer to the one that we had before when we had, the inductive donator, right? Now we just have a resonance donator. So this effect is a lot more prominent. If we wanted to, once again, we could, unravel, we could, show off that cation if we wanted to. It's totally fine. And I will do that. But once again, we see a polarity here, right? We see a polarity. Oops, not what I meant to do. Just trying to move this up. There we go. We see a polarity shining through where the enol ether has a cation located next to that heteroatom. So we have a cation here, an anion here. So when I do that same H plus ROH reaction, which actually, this is just a theoretical problem. This would actually do something else, but I will just, again, show it to you just to show it to you. Oh, no, actually, no, it will work. This will work, actually. This is just a very high level question. OR will go here and H would go here. Okay. So again, already all we know is polarities. We don't actually understand how the this is working, but we can already solve problems. And in reality, these are actually final level problems. So look at that. You guys just solved 2 final level problems. You guys are ready for the 118B final before you even taking the class. All thanks to understanding polarities. That's pretty cool, right? Right? It's pretty cool, right? Anyways, so I know this is a lot of information, so don't feel too, don't feel like you need to understand all of it immediately. Again, most of this is just to help you think about how the pi bond, how it interacts with its, substituents, how is it bonded, and, what does structure tell you? A lot of things structure tells you, right? A lot of this is food for thought. So if you have to, read through this a couple times, or, maybe even watch this portion a couple times, that's totally okay. That's totally okay. I think maybe this year I might start making my slides available. Yeah, I'll probably do that. Well, I'll have to see how I can make that work though. But yeah, so definitely I'll make sure you guys have access to everything. Cool. Now, this hyperconjugative idea, we can take one step further, as it's funny, right? We've been taking every one thing from every slide one step further, right? But we can take this hyperconjugative idea a little bit further, because remember, hyperconjugation is a stability thing, right? This was a stability thing. So if we had hyperconjugative effects, and we used to talk about that in terms of stability of a carbocation. So what do you guys think? Do you guys think that hyperconjugation also, relays as stability in an alkene? The answer is it's not a trick question. Yeah. So the more hyperconjugative effects you have in an alkene, you can argue that that alkene is more stable. So I'm going to draw all the different types of alkenes that you can have with methyl groups on them. And for a majority of these, we can answer the question of which is more stable just by looking at hyperconjugative effects. Let me just space these out a little more. I'll be honest, this is probably my third time making this, because I always do 2 runs, about one on average, like 2 runs before the final one, just so I can, the first one's always the one where I mess up the most and I just keep talking just to have a script in my brain. The second one is always one to kind of iron out those, and the third is the final. But all 3 runs, I've never managed to get this like in this kind of spacing that I like, which I guess is just something I have to live with. Anyways, if we look at hyperconjugative effects, right, we have 1 here, 2 here. Oh, interesting, we have 2 on a lot of these. So we'll talk about these guys at the end. We have 3 here. And we have 4 here. Okay. For a majority of these, right, where we have 0, we have 1, we have 2, 3, and then 4, we can say that the stability is going to increase with more of these donating effects. Okay, so more of these hyperconjugative effects, the better. And so stability will increase going this way. Okay. Now, there is another way that you might be taught, or you might be told about stability, and that is via the hydrogenation test. What is the hydrogenation test? So actually, the very first reaction you guys will learn now is that if I take an alkene and I throw H2 at it over a metal catalyst, what's going to happen is the pi bond disappears. That's because we put hydrogens there in its place. So before we only had 2 hydrogens here. Now we're going to have 4 hydrogens in total across those 2 carbons. This is a hydrogenation test, and it's not that hydrogenation to the product of it is what's telling us the stability. It's the heat that's coming off of the product that will tell us its stability, right? Recall that stable systems tend to be low energy systems. So a stable structure, right, of an alkene would be one that gives off very little heat. Or sorry, I gave it away, but it's one that has a low energy content. So when we break the pi bond and form the new H bonds, the amount of energy that should be coming out should be very low, right? If there's low energy content and we're making and forming new bonds, not very much heat should come off. So maybe a little bit of heat comes off if this is stable, right? If there is a high energy content in that system, so it's an unstable system, then there should be a lot of energy left over when we break and form new bonds. So a way to sort of summarize this, so the heat of hydrogenation should be very, very high if the system is unstable. Let me put it this way. So this is high and stability is low. So it's an inverse relationship. Okay. That kind of tells you then that the heat of hydrogenation, if stability is towards the left, sorry, towards the right, then heat of hydrogenation should be towards the left here. Okay. These systems down the left should have very high heat of hydrogenations. Heat of hydrogenation is not, again, it's not a absolute test though. It's not the only test you can use. You can use a lot of tests. It's just one that people like to use. And it's one that's like a good question to ask on an Orgo exam, if there is to be one. Okay. So yeah, it's something that sometimes shows up. But again, right, most of these are the ones that we can explain with stability of hyperconjugative effects. But it's these three in the middle that are a little interesting. The syn alkene, the geminal, and the anti. So I know that the normal nomenclature is typically cis trans. I don't like using cis trans because, well, actually, syn and anti are just way better terms, and we're going to use them a lot anyways. So it's better if you get trained to see syn and anti. Cis and trans is just really bad nomenclature, I think, and it leads to bad naming. I just prefer to use syn and anti. So that's just letting you guys know now that I'm just going to be this is what I'm going to do. I'm going to call them syn and anti just because we're going to use those terms a lot anyways. So the syn and the anti-alkene and the geminalkene, they're all di-subbed alkenes. So we can't really use the hyperconjugative effects to help us here too much. We could use heat of hydrogenation. That is a way to do it, but there's also another way that people like. It's a lot more, visually you can see it. For the syn and the anti, it's very easy to see, but you can make the argument that syn and anti, right, if we were to look at the methyl carbons, you can make an argument over the steric clash of the methyl groups. So I like to think of these as like helicopter blades. Just helps me think about it. But these helicopter blades would probably clip and this helicopter would crash and burn, versus this helicopter, these H's would never clip each other. So steric interaction can help you understand why syn is always less stable than anti. The harder one to see though, people have a harder time seeing this one, but people think that geminal tends to be the least stable of the three because, well, one, a lot of people confuse this to be a terminal. So terminal means that there is a CH2 end, right? The no sub and the mono sub. So actually, let me go ahead and put these down here. So mono, di, tri, tetra, right? A lot of people try to confuse geminal, the di sub, for mono and no sub because it has that CH2 end, but it couldn't be any further from the truth, right? It's not not at all a terminal. I mean, it is a terminal alkene, I guess, in a sense, but it doesn't have the same qualities as it, right? So people tend to think, oh, because of that end there, it's less stable. That's not always necessarily true. The other thing people kind of confuse is they think that, okay, so if syn has a lot of steric bulk, right, then that must be also true for the gem, right? Because the geminal also has this here. But actually the distance is, again, it's hard to see. I mean, you can also even just chalk it down to my drawing, but the distance here is actually a lot farther than the distance here. Actually, I know what I can do here. I can just use ChemDraw. I always forget this until I get to this point, that at this point in the video, I always like to open up ChemDraw. So I'm going to go ahead and do that. So we're going to take a quick detour to ChemDraw. So that's a geminal. Let me get rid of this. And then this is a syn alkene. Right. If I were to draw out the hydrogens, here, I'll draw them in and then I will zoom in. Okay, so cool. All right. These are just going to be H's here. Oh, that's not what I meant to do. Okay, let me actually zoom out for a second. Okay, this is good enough zoom anyways. So again, geminal syn alkenes. Maybe you can already see it, the point that I'm going to make in a second. Right? But if I were to actually look at the distance between the two hydrogens, even just from the bonds, very, very easy to see, even visually just from here. But this line is clearly smaller than this line. The actual distance is actually a lot farther between these two groups than these two groups. So in my opinion, syn alkenes should be less stable than geminal alkenes if you want to take the steric approach. Let me go back to my whiteboard. So in my opinion, which is a very good one, is a very good opinion. Why does it say that? I don't know. It should be that gem is way better than syn, and maybe gem is worse than anti, right? But a lot of professors like to simplify this by saying that they're the same, which is okay. That's okay. But I think that, if we're given data, we should go towards what that data says. You can actually even look up heat of hydrogenations, and I believe the heat of hydrogenation of gem is slightly lower than that of syn. I think it's literally 1. It's a difference of like 1. I think the values are something like, this is like 1, I think this is like 115. This is like 117. This is like 118. If you want, you can check me on this. You can check the NIST webbook, and you can look up the names of these structures. This is isobutene. This is clearly, you probably have to look up cis-butene for this one, and then trans-butene for this one. And you can look at you have to go to reaction data, and in reaction data, you can look at the hydrogenation, and that'll give you the heat of hydrogenation. I believe it's really, really close for these two, but it is gem that ends up being lower. Oh, actually, on that note, if you do look at it, just keep in mind that the way that we define heat in physics is a little weird. Heat that's given off, we define as a negative number because it's given off to the environment. So you're likely to see that this is like 117, and then this is like 118. And you might confuse this as saying, oh, 117, negative 117 is a larger number than negative 118. But remember, it's just a convention thing. We just say that this is negative because it's heat that's given off. We really look at the absolute value of the number, right? So don't, just a little reminder from physics that don't get confused by the negative numbers and all that stuff. Cool. All right. Anyways, just wanted to mention that. Stability of alkenes, though, right, in a hyperconjugative sense, right, goes by this way. But keep in mind that we have stronger effects too. So I didn't really mention this, but this inductive effect here, so this here being an inductive effect, this is not a terrible effect. It's not bad or anything, but it is not as strong as the resonance effects that we see here. So always keep this in the back of your head, right? Inductive effects are always weaker to resonance effects. Okay. Now there are always some exceptions to this, right? So maybe I shouldn't have said always, but in terms of what we've talked right now, resonance always has a higher effect. Actually, it might even be useful to remind you guys of carbocation stability. I'm not sure how many of you guys were taught this anyways, but carbocation stability, right? Primaries are so weak, they never form. Secondary is okay. It's not terrible. It's not great, right? It's a couple Rontgen. Shout out to anyone who gets that reference. Tertiary is better than all of them, right? But of these, there is just a better class of cation, right? There is the cation that's stabilized by a alkene, followed by a cation stabilized by an oxygen, right? And then followed by, actually, sorry, let me give myself a little more space here. That's also something I still just have not learned how to do yet. I still haven't figured out how to make my my spatial awareness is still very bad. Anyways, alkenes, right? Stabilize pi bond stabilized by or pi bond stabilizing cation is better than all of these, but it's not as good as, for example, an oxygen stabilizing that cation. Right, so if you have an oxygen next door, that's incredibly, incredibly great. Sorry, how am I going to do this? I guess I could just do this. This is fine. Okay. I'm trying to draw it exactly like this, but it's just not going to work. So I'll just do that. Followed by a nitrogen. Nitrogens, remember, are more nucleophilic. They're way more donating than an oxygen. So that's why we have that there. So a little reminder of cation stability, right? I put a comma here, but really it should just be that this is so much better, these guys here. And this is actually how cation stability is, tends to be organized. Hyperconjugate effects are always weaker than pi effects from carbon, and then pi effects from heteroatoms. Okay, so a little bit of a reminder how cation stability works there. Cool. So with all that information, I know it was a lot. It's definitely reasonable for you guys to take a break if you need to. Really, what I would focus on these last 4 slides is just, the concepts of structure, right, and bonding. So, really what I would take away from this is, the ethene side of things, the electronegativity aspect that we tended to take. I mean, we took it really far, right? This electronegativity aspect. I wouldn't really, if this slide was a hard one, don't worry about it too much. It's okay. Come back to this stuff anyways. And then this stuff here is really the meat and bones of structure, right? And how substituents can affect the dipolar moment on our structures. Okay, cool. Oh, I guess there's one last thing you can consider here. Rings are kind of a weird thing for alkenes. Most rings tend to be syn rings, right? So most rings are syn, in that, these 2 groups on the alkene, right, are going to be always the same way. So we don't really have anti-rings in the ring sizes that we care about. The ring sizes that we tend to care about in this class are 3 to 6. Nowhere in this range do we ever see anti-rings. Like when I say cyclohexene, all of you guys hopefully immediately think this. None of you guys think this, right? This is sort of like the anti-variant of cyclohexene. No one really thinks that, right? So we don't really ever consider, the anti-variant of rings. Another weird thing about rings is that this kind of alkene is known as an endocyclic alkene, right? It's inside the ring. This one is an exocyclic. Exocyclics tend to be less stable. So even though this is geminal, which I made the argument geminal should be more stable than syn, because the syn is inside the ring and this is outside, this tends to be just less stable for that reason. Okay, don't worry about too much why it is. It's got to do with conformation and stuff like that. It's just, I just wanted to mention just in case. That being said, though, it's not that anti-alkenes can't exist. It's just that the rings that we care about, only syn tends to exist. I think once you get to like 12 and up, anti ends up being the preferred conformation for any alkene. And so it becomes a problem if you look into medchem or probably medchem, and if any of you actually even care about this stuff, would be medchem. Medchem structures that we form tend to have alkenes of all kinds. The rings are huge. So it really matters if we can control whether it's a syn or anti-alkene inside the ring. So we'll learn different ways to do that throughout the course. All right. That being said, now that we kind of have a little idea as to structure and bonding, now we can get into how do we actually make alkenes, right? So before we play around with them and do our reactions of alkenes, right, we should know how to make alkenes. So how do we prepare them? And really the best way to prepare them that we know of now is going to be beta elimination. So this is 118A, right? So again, a lot of this video is I'll probably call this a review of, like relevant review of alkenes that you guys might want to watch before you watch anything else. But beta elimination of alkenes is going to be really our only way right now to make alkenes. So what is a beta elimination? Well, if I draw out my bromide here, right, let's use this, the simplest bromide we can think of that would work for this, right? A bromoethane. The carbon that holds the bromine is known as the alpha carbon, and any carbon attached to this is known as the beta carbon. So this is alpha because it contains the functional group bromine, and then any carbon connected to this alpha is a beta. So there's only one beta carbon here. Beta elimination means that on that beta carbon, we take off a hydrogen. So a nucleophile of our choice needs to take off this hydrogen. And then the electrons in that bond, right, of that H bond shift between the alpha and beta to form a pi bond. And to accommodate that pi bond, we kick off the bromine group. And what we're left with is an alpha beta double bond. And a protonated nucleophile. So why am I mentioning that there is a protonated nucleophile? Because once you realize it's a protonated nucleophile, a certain quality is sort of, elucidated about the nucleophile. If the nucleophile is protonated in this reaction, right, or it takes a proton, this is not really a nucleophile in the sense of just being a nucleophile. Really, we should define this as, what's it going to be? What should we really define this as? should be defined as a base. So really, we need a base here to do eliminations. And it might remind you why we use strong bases in the first place to do elimination, because the first arrow in E2 is an acid-base arrow. So because it's an acid base, we should use strong bases to attract those protons. Okay, so elimination is going to use a variety of strong bases. We'll go over those as we go through this. Okay, so that might be something you might remember from 118A, is that we use strong bases to pull off these protons and form alkenes. Maybe one thing you might not remember, though, is that elimination follows a very strict requirement known as the anti-periplanar requirement, or anti for short. So we can also just call this periplanar too. Anti-periplanar is just a really big term to say that the leaving group, which is bromine here, and the proton, right, which is clearly H here, they must be anti or opposite to each other. So again, these are just big fancy words that we made up, right? We couldn't just say opposite. We had to say anti-periplanar. They are opposite of each other in order for this reaction to work. So if I were to redraw this bromoethane and give it a little more pizzazz, in the sense that I can give it, a little bit of stereochemistry on all these H's. Remember, it's not incorrect to give an achiral center stereochemistry. We just don't do it because it doesn't matter, right? Achiral centers don't need stereochemistry because they're achiral. We don't care where things are in space, but it's still okay to give it to them. So don't think that this is incorrect or anything. This is totally fine. But with this drawn here, right, there are technically 3 hydrogens on this beta center. Right, there are 3 hydrogens on this beta center, but it is only the anti one that will be taken in this reaction. So for in this conformation, only the anti proton is taken. And so if we think about anti, right, very, very, easy rule. If the leaving group is in the plane, then the anti-proton will also be in the plane, just on the opposite side, right? So this is like in the plane down. This is kind of like in the plane up, in a sense. It is HA that is anti, and it is the one that is removed in reaction. So arrows would look something like that, right? Essentially what that means then is that if we form our alkene, then HB and HC are the ones that are left over. I know there's 2 protons on the alpha carbon too. You could draw them in if you wanted to. I'm just not doing that because, again, the point of this is just to say that HA is the one that's taken in this reaction, right? HB and HC are kind of just left over. Okay. So a good question that could arise from this is, okay, so I get why HA is taken as anti, but what about HB and HC? Are those guys always forbidden to be taken, right? Is it never possible to take those protons? And the answer is, in this conformation, it is never possible, right? If we have this current conformation, only HA is anti and can be removed. But here's the thing about linear alkanes. We can rotate, and rotation is always possible. So we could always rotate about this bond here, and we could force another proton to be anti. So I know that, rotation is probably everyone's favorite thing, and everyone's really great at it, but I'll still go over it for those of you that would like to practice and, a little bit of a reminder of how rotation really works, right? Actually, rotation is very simple. I know that it seems like it's very crazy and hard. It's actually a lot simpler than, maybe you had it seem in the previous class. One little trick I'll tell you guys is you can recopy the stereochemistry of that center. And what I mean by that is, we can recopy that there is a wedge down here and a dash back here and a planar bond there. All you have to do is just do your rotation correctly. So the only thing you have to, only rule you have to obey for rotation is just respect the direction. And what I mean by that is, let's say that I want HB to be in the plane now. So HB has to go to HA. That must mean that if HA rotates, it does not go here, right? It does not go on the wedge, because in order for HA to go on the wedge, it has to rotate the other way. HB to HA is a clockwise turn, but HA to HB is counterclockwise. So it wouldn't make sense that if HB ends up here, that HA ends up here, because again, that's just disrespecting the turn. So in order to respect the turn, HA must go to HC, or where HC was, and HC then must go to where HB was. Okay, sorry, this would be HC. And that's how we can respect the turn, right? And that's how we rotate correctly. So rotations aren't actually that bad. You just have to, again, just respect the direction you go in. And I know I went clockwise here, but you can go any direction you want, right? It's totally up to the reader or the drawer, right? Which direction they want to go in. I just chose for this problem to go in that direction. Maybe for the other one, I'll go in the other direction. I don't know. But we'll see. So you could have also have rotated HC, or I guess what I could say is you could have also have just rotated HC to where HA is, right, in the anti-position. And again, HA then therefore cannot go this way because that would be disrespecting the turn. It must go this way. And then HB must go to HC. Okay, so luckily here, I know that a lot of rotation issues was from like, RNS. Hopefully this kind of fixes things up for you guys. But now HB is the antiproton. And we have an anti-periplanar state where HB is now taken. Okay, so now what we're left over with is C and HA. Okay, so would it surprise you guys if I said that we could rotate one more time? Probably not. It's not a very surprising discovery at all, hopefully. But we can rotate one more time. And we can get, so let's try this again, right? So we've now eliminated HA, HB, so now we want to eliminate HC. So try this on your own, but right, if you want HC to go to HB, right? So HC goes here, then HB must go to where HA is, okay? Because that's respecting the turn. And then HA goes to HC. So now we have that HC is anti. And what we get is an alkene as such. Okay. Oh, sorry. It doesn't really matter which one's HB and HC, but what matters is that HC is not on here. Cool. So interestingly enough, right, the number of hydrogens here, right, on a linear alkane that has the ability to rotate will tell you how many anti-periplanar states you have, right? Like how many times can we be anti with a different proton? That is determined by the number of protons on the beta carbon. So a small little rule we can say is that the number of hydrogens on the beta carbon is equal to the number of, I'm just going to abbreviate AP here is anti-periplanar, but that's the number of anti-periplanar states, right? How many times can a different proton be anti to the bromine is determined by how many protons are there in the first place. So that's the case there. And in a sense, that means that the number of alkenes that we can form is also going to be correlated to that number. And this might seem a little bit weird to you guys, because if I sort of draw this out, right, if I draw this problem here, what I'm basically saying is that there are 3 different products here, but what's true about all those 3 different products? Oh, sorry. I gave these guys an extra tail. Not mean to do that. I'm saying that, we can technically form 3 different products here, right? But what is true about the 3 different products? They're all the same. So beta carbons that are CH3s, right? They will give us technically 3 different products because there's 3 anti-periplanar states, right? 3 possible anti-periplanar states, but they're all the same. They're all the same. So terminal alkenes are always our favorite alkene to react with, because we always get the same answer from them. So they're always the best. A good example that we can use for this, that I will use going forward for just explaining this concept right now, is we'll do this one here. We'll use this one here. We'll just change this one up a couple times. So once again, right, just to remind you guys, how can we determine where to react, right? This is the alpha carbon, and technically there's 2 beta carbons here, but only 1 beta carbon has hydrogens. That's what I want you guys to notice here. Only 1 beta carbon here has hydrogens. It is only this beta over here, so we can kind of ignore this one always because there's no hydrogens here. We're always going to get 3 possible answers. But the cool thing is that all 3 answers are the same. But there are still 3 possible states, right? Because there are 3 hydrogens here. So let's use this green color for this one. So there are 3 hydrogens, right? When the beta is a CH3, we get technically 3 products, although they are the same. So if we take this idea and then apply it to, let's say, the same substrate, but now I make this secondary. So now let's say that's a secondary again. This is our alpha carbon, and this is our beta carbon, right? How many hydrogens are on the beta carbon now, right? There are 2 of them. So what does that then tell us? Oops, did not mean to erase that. I'm going to just put this above just to make things a little more clear. Okay, so now there's 2 hydrogens. What does that tell us? How many products should I kind of predict there to be here? How many products should I predict are possible if there are 2 hydrogens? There should be, again, if the number of hydrogens on beta tells us number of AP states and the number of alkenes, there should be 2 different answers, or potentially 2 different answers. So let's kind of figure out what those 2 answers could be, right? Once again, I am aware that, right, I am aware of the fact that, these hydrogens are achiral, but we can still give them stereochemistry just to help us understand this problem. And this bromine is actually not chiral, or sorry, it is chiral. So it's good that we have the ability to use that as a wedge. So let's make that a wedge, right? Again, we have to obey the anti-rule, right? That the leaving group and the proton that we take off are anti to each other. So actually, let me keep the labeling so you guys can see it better. So alpha, and then any carbon connected to alpha is beta. So we'll look at that beta there. Okay. Let me also start using bases. So let's actually start using a base so you guys are familiarized with them. Good bases tend to be alkoxides. So this is a very common condition you'll see that promotes E2 or elimination, just an E2 style. So just a little reminder of what is a common reagent for that. But anyways, right? Again, if I look at the beta carbon, which proton is opposite to the bromine? Which proton is opposite? Is it HA or HB? Bromine's a wedge, then the opposite is dash, so it has to be HB. So we're going to take off HB here. And here's the cool little thing. If your hydrogen is already, or if your molecule is already an anti-periplanar in conformation, you can redraw the skeleton minus the bromine and the proton you eliminate. So redraw everything, and then just put a double bond between the alpha and the beta. And there you go. That is the anti-periplanar state. So we just copied the structure as is, and we got the anti-periplanar state. So look at that kind of alkene there, right? Maybe make a note in your brain as to what kind of alkene that is. But this is one of the possible products we can get. Once again, we have the ability to freely rotate. So I'm going to recopy the stereochemistry here, but now I want to rotate so that HA is anti. So where does HA have to go? HA is a wedge, but I want it anti to the bromine, so it has to be a dash. So HA goes to HB, so HA goes here. Again, HB cannot go this way. That's disrespecting the turn. HB has to go in the plane, which means the methyl has to come out as a wedge, just like that. Okay. And so now that we know how to do that, right, now we can say, okay, I'll use another common base here that we use, right? We can use this condition here, and we say, okay, this is going to give us an elimination off of this carbon, and we're going to specifically eliminate HA now. So now we're eliminating HA. Again, you can kind of ignore HA and ignore the bromine and draw everything. Now the carbon structure here, you might be tempted to draw this, but keep in mind that HB was here. So you can label this HB. Methyl is really pointing down here. So we draw it in like that. You can ignore the HB now. Oh, should have not drawn it like that. So we can ignore the HB. Okay, and then we draw the double bond between the, sorry, I know I said I would draw the benzodiazepines, the alpha and the beta. So we draw the double bond right there, and that's what we get. So again, I know it's a little bit confusing to see that, oh, the methyl, right? Just copy the structure as is. Actually, there's another way we could do this too, if it helps you guys. What you could do is you could draw out the H here. And then what we could do is, again, draw the carbon structure. So this would have been HB. One thing you could have noticed that is the methyl and the H here are opposite of each other, right? So methyl here is a wedge, H here is a dash. Stereochemistry of the anti-periplanar state is always preserved. So because this methyl is a wedge, it must be opposite to wherever this H is in place. And we can see here that the only place that this H could go is here, and therefore the methyl has to go here. I guess you could also make that argument anyways, is that on this beta carbon, HB is already pointing this way, so methyl has to go point that way. So whatever way works for you, but you can, use whatever you need to. But it doesn't really matter, because at the end of the day, you can kind of tell why these two are different and what relation they have. You can see that if the beta carbon is a CH2, what we get is a anti-alkene and we get a syn alkene. So when beta carbon is CH2, we get the anti-alkene and we get the syn alkene. So look at that. We are now seeing that there are two different products possible in this reaction, which is in congruence with our rule of number of H's on the beta hydrogen will tell us the number of alkenes, because that's the number of anti-periplanar states that we have. Okay. Now, between these two, it's not that we make both 50-50, right? Because remember what we said earlier? We said back here that anti-alkenes are more stable than syn alkenes. So really, the distribution won't be about equal. Otherwise, this reaction would not have, there wouldn't be a preference for this, which one we have in this reaction. We do see a preference. The one that's more stable, the anti-alkene tends to form a lot more, about 70, let's say 73%. It's a good number, which means that the syn alkene would be about 27%. Now, the fact that there are two possible answers here, right? Two possible diastereomers, or two possible stereoisomers, right? Where one is anti and one is syn, where one is sort of biased in distribution than the other. We call this a stereoselective process. So why is it stereoselective? Because there are two stereoisomers possible, where one is more favored than the other. But there is still two answers, right? Like, it's not like because it's 27, it's completely not there. The 27 is a lot, actually. You'd have to get rid of this 27% if it mattered for whatever reaction you were doing. Okay, so this is a stereoselective process because there's two possible answers where one is a lot better in distribution than the other. Cool. So again, if we ever react with the CH2, now we know that there is two possible stereoisomers, the anti or the syn, which leaves us with one last example. What if the beta carbon is a CH? So I'll use this blue color here. What if the beta is a CH? Oh no, what do we do now? Right, how many products do we expect to form now? Well, if our rule were to hold, number of beta hydrogens should equal the number of alkene products. And in this case, right, there should only be one alkene product. Okay, there should only be one. And we can actually even just draw it from here because, we can just see, okay, that just means that this is the only alkene possible. I do want to modify this example a little bit because we can get some, interesting information out of this problem. Okay, so let's go ahead, let's go to the next page and try this one out. So again, you might have noticed that I changed this problem a little bit, and you'll see why in a second. But I changed it so that there would be an ethyl down here. Okay, so we're gonna try two of these. We're gonna try this one here, and then we're gonna do the diastereomer of this reaction, which is this one here. Okay, cool. So of the two, this one's the easier one to work with. So we'll do this one first. Once again, I'm gonna just use a common base you might see. This guy here, I know this is a bulky base, and bulky bases do matter a little bit, but we'll talk about how they matter in a second. In this current example, they don't matter whatsoever. Okay, so this is just to get you in the into the mindset of what is an acceptable base for E2. Cool. All right, so I can do elimination on the substrate, and once again, there is a single hydrogen, and just ask yourself the question: is the bromine opposite to the hydrogen? Right. So sorry, I keep forgetting to do this. So this is the alpha carbon, and this is the beta carbon. Are they opposite to each other? The hydrogen and the bromine. The answer is they are. So what can I do for this elimination? Very easy. I can redraw the carbon structure as is, and there you have it. Because if this is already an anti-periplanar state, then the alkene is just going to form from whatever the stereochemistry is already available, right? In this case, the structure looks like this, so the answer has to look like this. Again, we could also use local stereochemistry, right, to help us out a little bit. And what I mean by that is, we can label this hydrogen here, which would be the hydrogen here. Notice how this hydrogen is a dash, and this hydrogen, or sorry, this ethyl group here is a wedge. That must mean that if this is a dash and a wedge, they're anti to each other. And if you look in the alkene, we notice that too, that they are anti to each other. Okay, so this is the only answer we get. This is the only isomer we form, and this is the one product. So why is it that I'm making such a big deal out of this? Well, let's say that I took the diastereomer of this problem and we try to do this again. Now, again, ask yourself the question, alpha and beta, right? Is the beta hydrogen here opposite to the bromine? So is the beta hydrogen opposite to the bromine? In this case, it is not. It is not opposite at all, right? Hydrogen is in the same plane as bromine. They are syn to each other. So elimination cannot just happen in this state here, right? We can't just get an elimination as is. We've got to do a little rotation. So that's okay though. We learned how to rotate just a second ago. So let's go ahead and get a little more practice on that. I like to rotate on the hydrogen side. Some people like to rotate on the bromine side. It's totally up to you. Just, whatever way makes you comfortable. I'm just more comfortable with this way. Again, I can copy the stereochemistry as is, and then just apply my rotation. I need H to go into the back as a dash. So H goes to the dash, right? So H is going to go back here. And again, ethyl cannot go to the wedge because that would be going in the opposite direction. So ethyl has to go into the plane, right? That's the only way it can go. And that must mean that the methyl goes to the wedge. So it's going to be here. Okay. So again, respecting the rotation, right? Respecting the direction. Now H is anti-periplanar. And when I do the reaction, I can just draw everything as is. So what I like to do is I just, again, draw everything in space as is. And then between the alpha and the beta, I just draw a double bond. So this is our answer here. And once again, we can prove to ourselves that this is correct using local stereochemistry, right? This H here, which is this H over here, right? That is anti to the methyl. So it should be anti to the methyl again here. So this is, again, the one product we get, right? It's the one isomer we get. And what's important about this is if we compare this guy to this guy, these guys are not the same whatsoever. So let's kind of put them next to each other. You can see that they're not the same whatsoever, right? The left side appears to be the same. So if I sort of split these alkenes in half, right? The left side appears to be the same, right? Where the phenyl group is on the bottom there and the H is on the top. But look at the right side. On the right side, the ethyl is on the top for this bottom one versus the methyl's on the top for this top one. Okay, these are actually two different stereoisomers. Okay, and we actually have names for these two different isomers for trisub and tetrasub alkenes. So you guys are familiar with syn, anti, and geminal for disub. For tri and tetra, we can't really use syn and anti because there's more than two groups. We use the easy naming system. So we use an easy naming system. I'll put it in red. And so how does easy work? Well, what we do is we basically look on each side and we assign priority to some group on the side. So if I look at, let's say, this carbon here, right? We have an H coming out and we have a phenyl group coming out. It's basically like applying RNS rules just to the group that's coming out of the alkene. So you compare H to this carbon. Carbon's always heavier than H. So this gets priority. Cool little neat trick. Anytime you see an H coming out of one side, the other group already wins on priority. So don't go past, if you just see H, it wins. Now just apply your rules on this side of the alkene to these two groups. Apply your RNS rules that you would for what will get priority over the methyl and the ethyl. Who is heavier, CH3 or CH2C? So CHH, right? Or HHH, right? So this carbon in red is bonded to 3 H's. This carbon in red is bonded to a carbon and 2 H's. Who is heavier, right? It's clearly the CH2. So this guy gets priority now. These are exactly the same, so we can apply the priorities as is, right? Once we figured out what the priorities are, we just make a comment as to whether they're on the same side or on their opposite sides. So are they syn or anti? If they're syn to each other, right? So the phenyl and ethyl here on the same side, we call this Z. A very easy way to remember this is Zameside. Okay, people remember it as Zameside. Okay. If they are anti to each other, they are E. And really, there's no like, I don't have a way of remembering this. If you just remember that Z is Zameside, you will remember that E is the opposite side. You know, actually, the funny thing is, when I think of Z, I would have thought Z would have been opposite sides because Z looks like they would be opposite. But, you know, I think the Germans are the ones who, they came up with the name because Z, I think, stands for Zusammen, which I think means same side. So, you know, no hate to them, but, you know, you have to think about it, right? Like visually, it feels like Z would be this one, but no worries. Anyways, syn is Z and anti is E, right? These are clearly different isomers. When you have a beta carbon that is a CH, you will only make an E or a Z. You only make one of them. You can't make both. And so this reaction here, where you only make one isomer and not the other. So the fact that, sorry, let me get rid of this stuff here. Okay. So the fact that we only get the syn and we only get the anti here, right? This is a stereo specific reaction. This is stereo specific because in this top reaction, we get 100% syn, 0% anti, so 0% E. And here, down here, we get 100% anti and we get 0% Z, right? So this is stereo specific. It's quite literally an all or nothing kind of deal here. Okay. So when the beta carbon is a CH, that's when the question becomes the most difficult because you can have only one isomer possible. Okay. So that's why really for this kind of problem, it's better to, for at least for the general rule, it's better to use, you know, this this achiral molecule here, or one where there's an achiral center, because then I can only, you know, it makes sense that it'll only be one. Technically for this one here, I have to specify whether it's dash or wedge, but we only get one product here. And again, this is stereo specific. Actually, I guess what I'll do is I'll draw in a stereochemistry. It's okay. You need to know the stereochemistry when two chiral centers are reacting in a beta elimination. You need to know the stereochemistry of both because this is a stereo specific reaction. Okay. Quite commonly, actually, this is how professors will catch you off guard on exams, is they will give you a reaction that looks like it shouldn't go. Or they'll give you one of these stereo-specific reactions, and a lot of people will draw the wrong isomer. They'll draw like if the answer is like in this case a Z1, sometimes people will draw the E1 on accident. And that really, I think that really comes into play with these kind of problems here, where the reaction isn't already an anti-periplanar. So this one up here, I think, again, is fairly simple because it's already anti, so you just have to redraw the structure. This one's a little more difficult because you have to rotate. But here's a little trick that works about 90% of the time that might help out a lot of you guys. There's really no name for it. It's just an observation you can make. But if you were, you know, stressed on time or strapped on time, one thing that you could do, so let's say that, again, this is not an anti-periplanar state, right? It's not already an anti-periplanar state because the H here is syn. What you can do is the following. You can draw the answer that you would get if this was anti. So let's pretend that this was anti. That would mean that we can draw it as is, right? So we can draw it like this, draw the alpha beta double bond and be done with it. Well, this would only be true again if this were anti, but it's not, it's syn. This is in a syn conformation. So how do we draw the right answer? You just switch one side. I did not anticipate having all that delete, but all we do is switch one side. So what I mean by that, we just switch like that. And now you have the correct isomer. Because the idea is that the syn isomer would just be the opposite of the anti, right? So if we're drawing what would be true if this were a syn elimination, to get the anti-elimination, we draw the opposite. So once again, how do I do this? If this is not an anti-periplanar, you draw the wrong isomer. So draw the wrong isomer, the wrong one, and then you just switch one side. In this case, I'm just switching the right side. And then you get the correct answer. Again, this will work most of the time. It's just that sometimes it won't work. There's always, every year, I get one person that figures out when it doesn't work. So, it's like, I have to put on the disclaimer, this won't work all the time, but it does work about 90% of the time. Actually, I can give you even a complex example of this, a complex example of this. Right. So these are the ones that you're bound to see on your exam because they force you to rotate or they force you to think about certain rules. But let's say that we got this problem here. Okay. So again, it helps to label your beta carbons and whatnot. I'm actually going to specifically make this over here, and you'll see why in a second I'm making it this. Right. Because when we label our alpha carbon, again, any beta carbons are any carbons attached to alpha. So it'll be beta here. And this will be beta here. But this beta has no hydrogen, so we don't have to worry about it for now. We only have to worry about this one. Okay. From this example here, you can see this is a pretty fairly complex one. The issue here is that while this H, again, is not anti, it's in a weird relationship with bromine because bromine's in the plane, but H is a wedge. So there's really no way to characterize this, right? There's really no way to say whether it's syn or anti. It's a little hard to make that argument. But once again, we can draw what this would look like if it were anti. So we can draw the wrong state or the wrong answer. So what that would look like is, just draw everything as is. So this would be the answer as is, right? It would look something like this. And we can use stereochemistry to prove this to ourselves, right? So in this state, notice how this methyl is a dash and this phenyl is a wedge. So they're anti to each other. We also see that in the this final answer here, right? They're anti to each other. Again, this would only be correct if the H were anti to the bromine in this case, but it's not. So then we just switch one side and we should have the correct answer. So I'm just gonna switch this side here. How did I know that it switched? Because these were syn, these phenyl rings were syn. Now they're anti to each other. Now they are not syn, okay? And then again, we should always prove to ourselves that our rules are working. We shouldn't just take them, for granted, or not for granted, but like just take them blindly. Actually, if this is wrong, that'd be good because it makes the point that I'm thinking which is that you should get really good at rotations. So rotations are better. Anyways, I like to rotate on the hydrogen side. So I'm going to rotate on the hydrogen side. You're also welcome to rotate on the bromine side as well. Just again, apply the correct, rotation. I realize maybe I should be doing that one too. So I'll try to do it next time. Or for this one, I'll do the bromine side rotation too, because we shouldn't neglect that side. But again, so if bromine is planar, then we want H to be planar as well, right? Because H has to be, opposite. The anti-bond is here, right, for this bromine. So H needs to go here. So if H goes there, again, phenyl can't go wedge. That doesn't make any sense. It's disrespecting the rotation. So phenyl has to go to dash. Phenyl has to go to dash, which means methyl, which is a dash, has to go to wedge. So it's going to be here. And so now we have anti-periplanar, which is correct. This is correct now. And we can go ahead and draw a double bond. This is a little bit confusing to draw the double bond, right? Because this H is going away and this bromine is going away. So you might be tempted to draw, like if you were to draw as is, you might draw something like this, which please don't ever draw this on an exam. I can't save you if you draw this on an exam. This is really, really wrong. And it doesn't really tell you what's going on, but we can use local stereochemistry to help us figure this out. So let's go ahead and draw the double bond and maybe even help ourselves. We can label alpha and beta, which I've been forgetting to do, so I apologize. We can label alpha beta just like that. And let's look at the alpha carbon. So the alpha carbon has a wedge phenyl group, and it also has a hydrogen that's a dash. So we could draw that in too, but I'm just gonna go ahead and draw the phenyl group in and the hydrogen in. You could also have switched these. It doesn't matter because you'll see in a second what I'm going to do here, right? It doesn't matter how I draw these in. The point is I'm just drawing those two groups in. So on the alpha carbon, I have a H and a phenyl group left over. So how do I know where to put these two groups? Well, if the phenyl is a wedge, then that means that on the beta carbon, whatever's a wedge should be on the same side, right? So phenyl is a wedge on alpha. So on beta, whatever is on the wedge here should be on the same side. So what does that mean then? That means that methyl is a wedge. Okay, methyl is a wedge. So it is on the same side as the phenyl. On the other hand, right, if this phenyl here is a dash on the beta, it should be on the same side as the H here, because that's dash, or it should be on the opposite side as the phenyl. That's a wedge. So dash wedge, right? They're at opposite sides. So they should be opposite of each other. So whenever you have these weird conformations where there's no real easy plane bond to follow and copy a structure from, just use your local stereochemistry, because the anti-periplanar state stereochemistry is going to be the stereochemistry of your double bond. That's always going to be the case. Okay. And so what we'll see here is that this might not look exactly like either of these, right? But again, if the phenyl groups are anti to each other, the methyl and the H are anti to each other, which one does that follow? And I'll even draw on the H's here. Looks like it follows the one that we made with our quick little rule. So look at that. That's great. So this little trick can work. Very, very simple. Very, I think if you just do a couple of practice problems, maybe we can do a couple of them actually right now to help you guys out. Not too crazy at all, right? Not too crazy at all. So let's go ahead and let's do a couple of these just because, I think if we do more together, you'll be more confident overall. But not too many, because I don't want this video to be too long. I try to cap these at three hours. But I obviously don't want them to be that long. Anyways, yeah, so let's go ahead and let's do another weird one. And, for a lot of these, I'm going to try to draw them as weirdly as possible, because I don't actually know how your professor will draw them, right? So I'm just going to draw them as weirdly as I can, so that, whatever you're thrown at, whatever's thrown at you, you can deal with it very easily. So actually, no, let's do this. Actually, no, whatever. I'm going to just do the one that I was doing right now. It's fine. No, let's not do that actually. Okay. So here's another one where the H is not necessarily in a very nice and comfortable spot, but that's totally okay. Because again, this is not anti, but if I look at this, I can do the wrong isomer. I can draw the wrong one, which would be drawing the skeleton. If let me actually label out alpha and beta again, sorry. So let's start this a little bit slower. So label out your alpha and your beta, right? And again, ask yourself, right? Well, first maybe ask yourself is which beta side has hydrogens? In all the cases that we've done, there's only been one side, for a good reason, because we'll get to the regioselectiveness next. But always, I've been trying to choose one side, and that's going to be this side here. Ask yourself, is that beta hydrogen opposite to bromine, right? Clearly not. I mean, H is a wedge, bromine's a wedge, so they're clearly not anti, they're not opposite. So we could rotate, that's totally fine, or we could just apply the rule, which is we draw the wrong isomer. So I'm just kind of drawing everything in place here. And then between the alpha and the beta, I can draw a double bond. So it'll be a double bond here. Again, let's just make sure that this will be correct, right? What can we use? We can use local stereochemistry to prove that what I've drawn is to some extent correct here. I would use probably the oh, this is weird. So these are anti to each other, but these are syn, but they can't be syn. So this is where it gets a little tricky to make sure. So here, actually, so let's do this then. For sure, we know the, oh, actually, I guess it wouldn't matter. Let's just go with this. So what I'm doing here is I'm noticing that the tert-butyl group here is anti to the phenyl group. So I'm going to go ahead and use that as my guide as to what would be the correct way or incorrect way to draw this. So yeah, let's use that. Let's use the plane as our as what gives us the information here. What I noticed was the H here would be syn to the ethyl, but that's kind of impossible if you consider everything else. So it's too much of a headache, so I'm not going to worry about it. It's okay. Just kind of ignore it. Just use the plane as our way to go here. And so if this is the wrong way, we have to do is switch. And what we get, I'm just going to switch the left side here, we get an ethyl up here, and we get a phenyl down here. Okay, so let's make sure that this is correct, right? I mentioned earlier that I'll try to do a bromine rotation because I've been doing a lot of H rotations lately. So I will do that. Let's go ahead. Again, I can copy the bond structure, I guess. So I'll just do that. And I'll just write in the H here. So bromine, I want it to go in the back because that's anti to this H here. So bromine has to go to dash. Again, H can't go to wedge. That's disrespecting the turn. So H can't go there. It's got to go down here, which means that this guy has to go up here. Terp butyl has to go up here. Okay. Terp butyl has to go here. Okay, cool. And so now this is correct. So let's go ahead and draw the alkene that would result from this. Once again, if I try to draw this as is, I kind of get a weird structure here. Actually, it's not too bad. We can draw this as is. It's not actually too bad. And what I get is this here as is. Once again, we can use local stereochemistry to help prove that what we drew here is correct, because we can say that, okay, if I ignore the bromine that's leaving and the hydrogen that's leaving, right, I have a terp butyl on the alpha carbon here that is anti to the ethyl on the beta carbon. So wedge dash, that's relationship that I see. And then I also see that H and H on the alpha and phenyl on the beta are anti to each other as well. And that's being, corrected. That's being, respected there. These two are the same because I see the same relationship. So this worked out. So these are the same. Yay, that worked out. But you can kind of see there that there was I had a moment where I was a little bit wary because if I had used the H here, right? I wonder, let's see if that would have mattered. Let's say that I said H, like I set the H as my reference point. That would force. Oh, looks like it doesn't matter actually. Because if I set my H as the reference point, so let me explain what I'm doing here. So let's say that I was saying, let's do the wrong way, right? And then I instead of focus on H and ethyl. So instead I focused that H and ethyl are syn to each other, which would have been here. That's actually the, oh wait, no, that does matter, right? Oh, it does, because this is the correct answer. Okay. So as you can see, this is great that we're doing this because I can see sometimes this fails. Sometimes this fails. This is really bad. This is not good at all. So I would say that only really use this rule if you find yourself on a time crunch, because you can see is that if I focused on the wrong relationship, I would have gotten the wrong answer. I would have gotten the wrong answer because focusing on the H, on the dash H and the dash ethyl tells me that, well, that would have given me the right answer immediately because this is the right answer, right? The wrong answer is where terp butyl and phenyl are on opposite sides. Okay. So a little concerning. It's a little concerning, but it's okay. So what I would then, for this particular one, I would say follow the plane. Try to follow the plane if you can. If you can't, then look at stereochemistry relationships. Like, for example, back here, if I followed the plane here, well, I can't do that because the plane is what's being eliminated on, right? So the plane, if the plane is what's being eliminated on, you have to follow, dash wedge stereochemistry. But if you're not eliminating on the plane, so you're eliminating on the dash and the wedge, then follow the plane relationship, and this rule should work out. It's okay. I know, these rules, there's so many of them. I hate them so much. Rotation is the best. So as much as I'm happy that this rule works 90% of the time, sometimes that 10% can leak out. So let's try to stick with rotation as much as possible. But hopefully you guys have been getting a lot of practice with rotation. So let's just do one more just to be safe. Just to be safe, right? Doesn't hurt to be safe. I realize I've been using a lot of the same structure, which might seem a little not creative, which you're right. I mean, if anyone's thinking that, yes, it is not very creative. But you know, the more we do this, the more you'll be comfortable with it. Did I put anything? No, I didn't. I forgot. I should be putting bases here, but it's no big deal. Yeah, go ahead and try this one. Again, label out that alpha and the beta. You could label out this beta, but again, no hydrogen, so who cares? And what we get, hopefully, again, you see I'm doing a syn-H, relationship. So let's go for a wrong structure. A wrong structure would be one that follows the exact positioning of everything on the plane here. Just like that. And then it's, to get this correct, we just got to switch one side. So I'm going to switch the right side here. So we have what we're saying should be correct is the side where we have both phenols next to each other. So let's see if that works. Let's rotate on the bromine side, because again, I've been neglecting that side just a little bit. So that means that there is a wedge H here. Okay. So again, I need bromine. If the H here is a dash, I need bromine to be a wedge. So bromine goes this way, which means that H cannot be on the dash. That would be impossible. H has to be on the plane. And therefore, the phenyl has to be on the dash. There you have it. Okay. Now, once again, this is like the correct way. So we could go ahead and draw the alpha beta double bond, but it's a little hard to see what's going on here. So let's go ahead and use our stereochemical relationships. So again, on the beta carbon here, it doesn't matter that I chose the beta carbon. I just chose a carbon at random, but I know the beta carbon has, after elimination, so taking off this H and this bromine, after elimination, it's going to have a phenyl and this terbutyl. So when we think about the alpha carbon and what should be on there relationally or related, there's going to be an H and a phenyl. Now, again, just use stereochemistry to explain things. We can either focus on the terbutyl or the phenyl, doesn't really matter. But this is a dashed phenyl, right? A dashed phenyl. So who is that related to on the beta carbon? The dashed phenyl is related to the terbutyl, that's a wedge, in the sense that if it's a wedge, that terbutyl and the phenyl's a dash, they should be anti to each other. Right? And again, if both the H and the phenyl on the plane like that, they must be anti each other as well. And these are the same. These are the same. So yeah, I think it works as long as you, so that rule of mine works as long as you focus on the plane, right? Versus when, the plane is being eliminated on, then you can focus on dash and wedge. So maybe we should do just one more. Doesn't hurt. I'm just going to, okay, let's do this then. So we get an example of where it's not on the plane. Actually, let's put H here. Okay, let's do that. So once again, label your alphas and your betas just to help keep track of everything. Ask yourself, is that beta hydrogen, sorry, this one here, is that anti? Bromine's on the plane, H is not on the plane, clearly not anti. So let's try the rule. Let's draw the wrong one here. So how can we draw the wrong one? Just again, copy the structure or use, stereochemistry, like relative stereochemistry. The relative stereochemistry here, I would say, so you're forced to use relative stereochemistry. Otherwise, this won't work, but that's okay because we can use the phenyl. Sorry, yeah, the phenyl and the terbutyl, they're syn to each other. So yeah, actually, that's what I would say. If you cannot use the plane because the plane has, bromine or H or the beta H on it, then use the relative stereochemistry around. That would then mean that H and sorry, yeah, H would be on the other one. Sorry, H would be here. H on the alpha carbon here and the beta carbon ethyl have to be on the same side, even though they don't really have a relationship, right? Because this is a dash and this is in the plane. We really would not have known that until, you know, we assigned that stoichiometry there. Okay, cool. Again, in order for this to be correct, we have to switch this. So I'm just going to switch the right side. And if we did this correctly, right, this should be the correct isomer. So let's go ahead and let's apply a rotation. I'm going to go back to applying H side rotation, just because I'm, you know, that's what I'm comfortable with. And again, so we want H to go in the plane. So H is going here. So if H is going here, there's no in the world that ethyl is somehow going to the dash, it has to go to the wedge. I guess a good way of thinking about it is that if the dash is going to the plane, or if two bonds are, if you're spinning a bond to another bond, actually there's no easy way for me to say this. The fact that the dash thing is going to the plane thing means that the plane thing has to go to the wedge. Like it has to go to the other thing that hasn't been interacted with, I guess. That might have been really confusing. So maybe you guys get my point. It's no big deal. Anyways, this means that this has to go here. And then on here will be the phenyl group. So now this is correct. And when I draw my alkene, which again, this is the alpha and this is the beta, right? The alkene will look like this. Using, you know, relative stereochemistry will always work if you're already an anti-periplanar, because we can just say, okay, on the beta carbon, there is a phenyl and an ethyl. And there is an H here that I'll draw in. H and phenyl on the same side because they're both dash. And terbutyl and ethyl are on the same side, which if we look at this, exactly the same. They're the same. Cool. So hopefully those examples helped you out. These are truly going to be the hardest E2 problems you could get typically on your midterm one. So it just helps. Although it's kind of funny because these are always, not that they're low yield. They're low yield in the sense that you're only guaranteed to get like a couple of them, but they're always going to show up. If that makes sense. So I guess in a sense, it's a high yield question, but it shows up like as a one or two questions show up like this. Cool. So the last thing we have to talk about before we get to the special type of E2 is just going to be the fact that we've been doing examples where I've been forcing one beta carbon to react. So for example, a lot of our problems look like this, right? Where only one beta carbon could react. So alpha and beta here. So only ever one could react. So it didn't really matter what I used as my base. Could have used anything, right? Because this beta carbon has no hydrogen, so we never worried about it. We always worried about this one. But we can have regioselectivity if I introduce hydrogens on two different beta carbons. So let's say I had this example here. We have alpha, we have a beta 1. Use this color for beta 2, right? How can we inspire regiospecificity, right? How can I select for only one side reacting? It's very simple. If you want to react with the more subside, we use a small base. And again, so this is a CH. So how many products should arise? Only one. And since it's achiral, we don't have to really, since one carbon is achiral, we don't have to really worry about which one we draw. It's only when both carbons are chiral that it matters. We always get that. And if we wanted to react with beta 2, which is the less subside, we use a large base. Now, here's the cool thing. If I just show you what the large bases look like, you know what they should look like, and you know what is a small base, because everything else is a small base. But typically, there's two sort of prototypes to what is a large base. There's terbutoxide, which there's many ways to write it. I'll write it in all the different forms down here. You can see them in these three forms here. Other one is going to be LDA. So it's like this. Lithium diisopropylamide. That's what we call that. hopefully you never have to actually get this written out, because you can see it's kind of a nightmare, because you'd have to use CH3 2 CH, and then this would also be 2 N. So it's a pretty long name, this one. Hopefully no one ever makes you guys actually look at that. It's kind of disgusting. Right. And minus. Okay. Sometimes you'll see this like countered by an ion, like lithium or something. Or actually, you probably see Na for this one. Sodium or potassium. Potassium is, that's actually the one that I have in my lab. It's potassium. Likely what you'll see other time. But if you know that these are what the bulky bases looks like, you kind of know what counts as a bulky and not a bulky base. For example, ethoxide looks nothing like these two, so it's probably small. But isopropyl oxide, isopropoxide looks kind of like tryptoxide, so it's probably considered a big bulky base, right? So kind of the idea you take there. Again, this beta carbon is a CH3. So what do we get? We always get one alkene, although technically there's 3 different, there's 3 different alkenes, but they're all the same. We get something like that. Okay. We can make a couple comments here on the fact that this is a stable alkene, right? Or it's the more stable alkene, which means that it is something we call the thermodynamic product. And we have a name for this, it's state sev. So I guess we could also say that it's more substituted too. On the other hand, this is the unstable alkene, which is unstable. We can typically refer to as a kinetic product. There's typically a reason, I'll go over this in a second. There's a reason why we make this distinction. We have a name for that, Hoffman. We call this Hoffman because this dude Hoffman did a lot of stuff with less subalkenes, and is the less subalkene. Now, of these terms, you're probably used to most of these. You probably understand what stability means, what Zaitsev-Hoffman means, and what more sub and less sub means. But this idea here might be new. Thermodynamic and kinetic terms are just, thermodynamic is like an overall very stable product. The idea typically, if you were to look at like a reaction diagram, is that thermodynamic products tend to start, tend to have really high energy barriers, but they always result in very low energy materials, because that's thermodynamic. Hoffman products, or kinetic products, tend to have lower energy barriers, but the product ends up being higher in energy. So kinetic products form faster. They're kinetically favored, right? They're faster, but just because they're faster doesn't make them stable, right? They tend to not to be stable. Another way to think about this is that the intermediates for kinetics tend to be very, very stable, right? The intermediate state, which is this state here, is very low compared to the thermodynamic state. It's very high. Don't worry too much. We'll care about this more midterm too, but that's where those terms come from. So the fact that this is more stable means that it's thermodynamically favored. And the fact that this is unstable means that it's kinetically favored. Okay. And that's how we can control for that. So sometimes when you do elimination reactions, you can kind of just look at the, what I would do if I were looking at a problem is immediately look at the base type, so I know what to worry about, right? Actually, let's go through a problem where we have all the components that we currently talk about. And then, we can, worry about, kind of make a thought process for ourselves. So what I would do if I were, taking an exam and I were looking at a linear chain alkane, what would I look at first? You can look at 2 things first, right? You can first kind of look at the alpha beta carbons. So I think I would immediately, you can label them out if you want to. It might help out the first couple of times to label them out, to think about alpha and beta. And, label them if they have hydrogens, right? Like, for example, if this beta hydrogen or this beta carbon is phenyl, there's only one beta site, so it doesn't really matter what you do, right? I would only really label them if there's 2 different beta sites, so that there's regioselectivity. If there is regioselectivity, so the fact that beta 1 is different from beta 2 here, so beta 1 is different from beta 2, right? Then you can think to yourself, okay, what am I using, a small or a large base, right? Beta 2 is going to be good for a large base, and beta 1 is going to be good for a small base, right? So then we kind of look at the conditions, right? This is clearly a small base, so we know the reaction is going to proceed on beta 2 there, sorry, beta 1 there, and beta 2 is, this is the large base, so it'll prefer that one there. So that's sort of the thought process you can take in any, you don't have to do in the exact way that I did it, but just things to think about, right? Because sometimes you might see something complex like this, where there's 2 chiral centers, and you gotta think about, oh, damn, this beta is a CH, so there's like one product, I have to get it incredibly correct. But then you look at the base and you're like, oh, wait a minute, this is a trick question, because it's a large base, so I only worry about the CH3M there, and that will always give me a terminal alkene. So I don't have to worry about the chiral center, other than that it's still there. Okay, only care about the chiral center if, right, we have the reaction on the 2 chiral centers there. Okay, cool. So this is already an anti-periplanar state, so all I have to do is just draw what I saw, right? Keep in mind, you are never, ever, ever forming this one, right? You're never forming that. Cool. So I know that was a lot of information. So definitely, if there's a time to take a break, it's now. Time to review your notes, it's now. But that's the majority of E2. There's only one more thing that we have to cover for E2. And it's quite an exception, actually. It's sort of like the exception of the E2s. And that's going to be rings. Because one thing that we've been kind of abusing without realizing we were abusing it was the fact that we get to rotate. So anytime we had hydrogens, we got to rotate, right? Well, guess what? If I'm doing a problem with a ring, rings can't rotate. Not at all. So these bonds here are prevented from rotation. So what that means to us then is that, let's say I have a bromine here, right? And I do an E2 reaction. In the past, we just said, oh, as long as there is 2 hydrogens here, right, I will have 2 anti-periplanar states because there's 2 hydrogens, right? Well, that's not the case, because without rotation, one of these hydrogens, right, cannot become anti-periplanar. So now, before you do anything with a ring, you have to always make sure anti-periplanar is being satisfied. Because what used to be that there would be, 4 hydrogens here that could participate in anti-periplanar elimination. Now there is only 2 of them, right? And so this is the wedge. That means that only the dash protons here could participate. Only those guys could. These red guys here are never allowed to participate. Okay? So the product is the same regardless, right? But let's say I eliminated on the right side there. The red proton is the one that stayed, right? The green proton is the one that got taken off. So when you do a problem with a ring, with like any kind of ring elimination, the first thing you have to answer before you answer anything else is which protons are anti-periplanar. So you might remember back here before, right? I did a lot of stuff. I looked at, what beta carbons were there? Did they have hydrogens, right? And then did it matter? Like, was there a regioselectivity between, more sub and less sub? And then look at the bases. All that's kind of, that process is kind of thrown out the window in the sense that the first thing you always have to look for are, well, one, is there beta carbon hydrogens? And 2, are they anti-periplanar? Okay, so let's kind of do one problem on that. Right, we can do this one here. So again, I can actually, only just say base here, because first things first, ask yourself. Actually, we can leave this ambiguous for now, because first things first, ask yourself, what are the alpha and beta carbons? So this is alpha and this is beta. And are there protons there? And are those protons anti? So take a second to think about that. So the answer is there are hydrogens here. Okay, so there's this one here, and on this one we have these ones here. Okay, so there's definitely hydrogens on both the alpha and the beta, on both betas there. So beta 1, beta 2 could possibly have a difference. But then the question becomes, right, are there any anti-protons? So if bromine's a wedge, are there any antis on either beta 1 or beta 2? In this case, an antiproton would be a dash, and both of these guys have dash protons. So there can be a regioselectivity, right? And there is, because this is a more subcarbon, this is a less subcarbon. So we can have a regioselectivity present, right? Whether I use a bulky base or I use a small base. Okay, so you can solve the problem if you want. In the small base case, right, do we react with beta 1 or beta 2? Going to react with beta 2. right? But if we use a bulky base, it reacts with beta 1. So react on the left side there. Keep in mind that if I'm doing an E2 reaction on a side, right on one side, the other side is not affected. So this stereocenter should always stay intact, should never change. I notice sometimes what people will do is they'll draw it out as planar. This is terrible because it's understood what you meant, but by taking away the stereochemistry here, you make it seem like you're saying that that center could be dashed or wedged, and that is very, very wrong, right? So make sure to keep in mind that if you're not reacting on the center, don't change the stereochemistry at all. Okay, so in this case, right, stereochemistry, or sorry, this case, regio specificity did, or sorry, regio chemistry did still exist, right? Because both beta carbons had hydrogens that were anti. But what about this problem here? Okay, so go ahead, ask yourself the question. This is alpha, and what would be beta? It would always be these carbons here, beta 1 and beta 2. Right? Are there hydrogens on those centers, and are they anti? So pause if you have to and try that out. Hopefully you did pause and try it out, but there are hydrogens for sure. So I'll draw them in. And again, ask yourself the question, are the protons anti? So this is really important to ask because on beta 2, right? So if bromine's a wedge, we need a dash proton. Beta 2 definitely has a dash proton, but beta 1 doesn't. Beta 1 has a wedge proton. It's syn. And there are no protons on beta 1 that are anti. So actually, beta 1 cannot participate in reaction. This question, which appeared to be regiochemically, it appeared to be one that was testing on regiochemistry, it's actually more of a trick question, or more of like it's a stat check. So make sure you understand that, oh, the only time I have regiochemistry is if both sides have an antiproton. In this case, only beta 2 has a proton that's anti. So we only react on beta 2, regardless whether I use a small or large base. Okay. And so in this case, I can use small or large. My answer is always this one here. So this one always tends to catch people off guard because they think that if it's small or large, there is a difference, but there isn't, right? Because there's only one beta carbon that we react with. It's kind of been like, back here when I was talking about how, it didn't matter whether I used terpetoxide or if I used a large, a small base like ethoxide. There's only one beta carbon to react with, so there's no regiochemistry. Regiochemistry only exists, right? Two different bases have a different effect only if the two different beta carbons are readily available to participate. In this case, beta 1 could not participate because it has only a syn proton. It has a syn proton. So if I kind of draw the super example, if I have this example here, again, you can pause and try this on your own. So definitely do that if you want to. So hopefully for those of you that wanted to, you pause and try. Beta 1, beta 2. You can also even make the argument that they're the same. So you could focus on one side, doesn't really matter. But if I looked at these guys, right, do they have syn or antiproton? On this side, I have a dash proton. On this side, I also have a dash proton. Is that anti to our bromine here? No, neither of them are anti. So if neither of them can participate, doesn't matter if I use small or large. This is always going to be NR. So our first NR problem, that's crazy, right? There's a possibility to have NR, right? And this is what makes rings a little bit frustrating, right? Because you have to, I guess it's not that frustrating. You can kind of, in a sense, I guess you could memorize some of these, but you should never memorize. Do not memorize. I'm not condoning memorization. It's not good for you. Anyways, so it's a possibility. So I'll leave you with one last ring example. It's always a good one. I love this one. Here's what I'll tell you. If you want to do well on this problem, you have got to label your beta carbons. Maybe that gives it away. But you've got to label your beta carbons if you want to do this one right. So I definitely want you guys to pause and try this one. And actually, not only that, I want you guys to also answer, is there a regiochemistry? Or is there like a regio, like is it possible to have regio here? Is it possible to have regio here? So go ahead and pause and try. Right, label your alphas and betas. Can elimination occur? Are there any antiprotons? Can elimination occur? Doesn't matter what base I use. Try to solve all those problems. Cool. So I'm really hoping that at the very least you guys tried this problem on your own, because it's a great problem to ask, great problem to try. First things first, label your alpha and your betas. So we have an alpha here. Remember, any carbon connected to alpha is a beta carbon. So clearly this one, and maybe many of you labeled those two. So it's possible that maybe, just out of muscle memory of these guys, you labeled those two. So let's try to solve the problem with just these guys, right? If we try to solve it with these guys, the answer we might get is that, okay, there is an H here, right? And an H here. And we ask ourselves, okay, are there any anti-H's to this dash H, or sorry, dash bromine? Dash bromine requires a wedge hydrogen on the betas, neither of which are the case. So this would not work. So a lot of you probably came to the conclusion this is NR. In fact, though, this does have a reaction. And again, it stems from the fact that you must remember that any carbon attached to alpha is beta, which means that this carbon here, sneaky little carbon, is also a beta carbon. And this carbon here has 3 hydrogens that are freely rotating, all of which at any point in time could potentially be anti. And what we're left with is this here. What we get is this alkene here. So very sneaky example, this one, because it really forces you to think. And, it kind of pushes you to realize that, you're not always going to get the, examples that you might see. Right? So because there's only one beta carbon that can participate, that answers our question as to whether there's a regiochemistry, because regiochemistry requires 2 different betas, right? There's only one beta that's possible, so it doesn't matter if I use small or large. Okay, won't matter at all. Now, if I were to flip this example on its head, and what I mean by that is, let's say that I have this the same, but now I change this to this, right? Now we can start to think a little bit as to what an answer could be, right? We do now have a, actually, let me not say anything. Go ahead and try this on your own. So pause and try this. Hopefully you did that, paused and tried. Maybe this time you labeled everything out. You even caught beta 3 here. Right? Now, when we do this problem, we do have H's that are interesting, because bromine being a dash on this alpha carbon means that hydrogens on all the betas just have to be wedge. And what do you know? This hydrogen's a wedge. This hydrogen's a wedge. And there could, at any time and point, be a bromine that's anti on beta 3. So technically, all 3 hydrogens could react. One thing to note is that technically beta 1 and beta 2 are the same here, or they're kind of the same. Actually, I'd have to draw up the answers. But beta 1 versus beta 2, they're the same sub. But beta 3 is not the same sub. It is, CH3, right? These are CHs. So there now is a perceived regiochemistry. So if I use, let's say, a small base, let's use propoxide for some reason. That would mean that we react on one of these 2 centers here. Sorry. So we react either on beta 1 or we react on beta 2. So, okay. So it actually does kind of matter, because these are not the same molecules. They are mirror images of each other. They're actually, if they're mirror images of each other, what would we call that? There's a name for that, right? It's an enantiomer. They're enantiomers of each other. So that's interesting. So we can make enantiomers here. If we use a large base, though, then we only get one answer. we get this one here. Okay, cool. So that should actually probably cover every single ring example, but don't think that these are the only ones. You know, someone can always think of a clever one eventually. But yeah, that's E2. And again, a lot of information E2 is, but there's for good reason, right? There's so many ways we can make alkenes. One last thing that I would like you guys to think about is the fact that really aside from this here that is stereospecific and we can get so much, we can get one really specific alkene. Trisubs and tetrasubs are really the only ones where we can make a very specific alkene. When it comes to the disubs though, again, of the two, there is one that's clearly major, right? The anti-alkene. This is clearly major. So as of right now, there really isn't a good way to make syn alkenes. Syn alkenes aren't going to be major until the end of 118b. There's a reaction we learned to make it a little more stereoselective towards the syn side. Not exactly, not going to be exactly stereospecific, but it'll be stereoselective. But we do have stereospecific processes for E or Z. Okay, so trisubs, tetrasubs, very easy for us to make one of the two. Anti or syn, it's going to be more on the anti side. So depending on how your professor defines major product, it might only be just that you have to write the anti. Cool. So that is E2, beta elimination. Fortunately, there's one more, but this beta elimination is really easy. It's really, really easy. Okay. The last beta elimination, it shouldn't take us very long. It's going to be E1 beta elimination. So what is E1 beta elimination? Just a bit of a reminder, right? E1, unimolecular, means that the leaving group has to leave, right? I don't know what I was going to say there. Carbocation, that's the hallmark of the unimolecular mechanisms. Carbocation forms, and there are typically two sort of destinies, right? One is that a nucleophile adds on. The other is that we get a elimination. And so how do we define alpha and beta for these guys? Alpha is always the carbon that holds the cation, and beta is always the next door carbons. Okay. In the case of E1s, we will pretty much always get Zaitsev products. Pretty much only Zaitsevs. So there's really no worry for the Hoffman. So that's the thing with E1s is you pretty much only get a Zaitsev product. And of the Zaitsevs, you pretty much only get these stable Zaitsevs. So actually, you're probably only ever getting the anti-alkene, the syn alkene. In E1 conditions, the syn alkene tends to isomerize. It tends to isomerize into this anyways. When it comes to bromides though, like alkyl halides, we don't really do the E1 on alkyl halides because the E2 is just so much better. So this kind of sucks. E2 is better. But there is a molecule of which, E2 is not very much an option. And those are our alcohols. So look at that. Alcohols do have some relevance. Alcohols can be dehydrated. And dehydration tends to occur in highly acidic and high temperature conditions, sorry. So very high temperature. And once again, we tend to only make the Zaitsev alkene. Okay, so we tend to only ever make the Zaitsev alkenes. And again, the stable of the Zaitsevs. Again, in these conditions, even if you made a syn alkene, it will likely isomerize in E1. It will likely isomerize in E1. Okay, like it's pretty much always the case that it will isomerize. Okay. So all that you need to remember about E1 dehydrations is that because we have cations can do funky things. One of which is that cations like to rearrange. So to go through the mechanism a little bit, right? How does this work? Right? Alcohols, one thing I'll tell you is that sometimes you'll be stuck on a mechanism you don't know how to proceed. Just use your context clues and what you know from just mechanics of acid and base to help you. Like the fact that this is an acid means that there must be a base on this molecule that likes acidic things. In this case, it's an alcohol. So you can always just guess that you have to do an acid base here like that. Alcohols, lose, once you turn them into water, they kind of lose that water. And on that same carbon that we lost water, we get a cation. Just remember that if you ever form a cation, just look next door, right? Look alpha and beta and look and see if you have, a better position to be. One thing I'll tell you is that you don't actually have to do a shift here. You could if you wanted to, because really, there's really two fates, right? One fate is that this hydrogen can rearrange, to form the tertiary cation. And then we could do like, so the H went there, then we could eliminate that H if we wanted to form the Zaitsev alkene. The other thing is that actually a base could have just taken this hydrogen in the first place and just formed the alkene from here too. So E2 is not always a requirement, or sorry, rearrangement's not always a requirement for E1. As long as it's next door, it's good enough. Right? So we still get the same Zaitsev alkene. Really, where this will matter is if the tertiary position is a little out of reach. So let's say we had this example instead, and you can go ahead and draw this in if you wanted to. Just for the sake of time, I'm going to skip forward a little bit, but we're going to form a cation where that alcohol is, right? And so again, if we looked at the two beta carbons here, right? So again, this is alpha, and then we have beta, let's say beta 1 here and beta 2. Again, if we're always going for Zaitsev, the most sub, which beta do we react with? It's going to be beta 1. So we can go ahead and draw. So beta 1 is a CH2, so it'll be the syn or anti. But again, of the two, anti is more stable, so I can just draw it as is. Oops, sorry. I kind of gave away what I was getting to, but we can have this here, right? This syn, or sorry, this anti-alkene here. Well, the thing is that in acidic conditions, you can actually get a reprotonation. Okay, this is actually also a reaction you're going to learn coming soon. But alkenes will isomerize in heat, like I mentioned. And the way they do it is that the pi bond just re-picks up a proton. So it's sort of like the opposite of elimination, right? Elimination says, okay, I take this hydrogen and I give it electrons to form the pi bond. Well, the pi bond just says, okay, let me take that proton back. And so as of right now, there really is, it may not make sense why the cation goes in one place or the other, but you can think about it this way. If we go here, we go back to where we were before, which was not the happy spot. But if we go here, we are very close to the happy spot, right? And the happy spot being the fact that we can make a tri-sub alkene. So don't be afraid to move over a couple carbons, like a carbon or two, to get to your stable alkene. That is literally what alkenes do in acid. In acidic conditions, alkenes will always isomerize to their more stable form. That is just a fact. So this is what I mean by when I say they isomerize in acid. Acid is like, non-nucleophilic acid is like the best condition for a cation. It's like what we call like a way to sustain a cation is to put it in acid. Okay, so don't be afraid to use that. They definitely want to be in those conditions in the first place. Okay, so we can do that. The last example I will leave you with that's pretty cool when it comes to these kind of reactions is the following. So we can actually dehydrate this alcohol. And again, we can go through this step by step. This alcohol will get protonated. So we'll make OH2 plus here, water. Again, anytime water forms, we're always going to kick it off. And then we form this cation here. Now, it might be really tempting to say that, okay, this cation, what's going to happen is we're going to get a hydride shift because when I look next door to the cation, there's a tertiary center. That's not a bad thought to have, right? I mean, we've trained you guys to have this thought at this point. But something else happens, and it kind of, requires that you guys remember something really specific about cations or specific about shapes, and the fact that, squares and triangles are very, very unstable, very, very unstable. If you give them a reason to expand to another shape, specifically a pentagon. So if you can allow a square to go to a pentagon, it will very happily do that. It will do it instantly. Same thing with a triangle. If you give a triangle a reason to turn to a square, it will do it very quickly. So whether it's triangle to square or square to pentagon, it will take that chance anytime it can get. So in reality, even though it feels like you should do a tertiary hydride shift, what's actually going to happen is a ring expansion. And I will number these atoms for you. I know it's always a hard thing to see, but let's say we number this 1, 2, 3, and 4. And then we'll number this new atom. So anytime you expand a ring, obviously it's going to go to make a larger ring size. So we're going to 5 for sure here. So I can go ahead and I'll go ahead and just number this to 5 because that is the case. But it may not be obvious how these things number. So I'll help you guys see how I see these expansions. Okay, so 1, 2, and 3 kind of stay the same, right? You see how 1, 2, and 3 kind of don't change. So 1, 2, and 3 will do this. They stay the same. What's changing here is that the 3 to 4 bond is breaking, right? Because we're moving it. That's what's shifting. 3 is breaking its bond with 4, right? So 3 is losing its bond with 4 when we make this movement, and it's making it with 5. So although you might want to say 4, 5 like this, that doesn't really make sense because 3 and 4 are losing their bond, right? Because we're shifting it over. Really, 3 is forming a new bond with 5, and 4 already had a pre-existing bond with 5 anyways. So 4 has a bond here. So 4 has a bond of 1 and 5, and it used to have a bond of 3, but it lost that bond. Another way to think about it is that this bond used to exist, and then we incorporated 5 by breaking the 3 to 4 bond like that. Okay. That's just a way to think about it. 5 has a methyl coming off of it, so we'll add that methyl in. So this is also something people kind of get confused as they see an ethyl and they think an ethyl should show up here. That's not the case because one of those carbons in this ethyl, quote unquote, turned into like a ring carbon. So there's really only a methyl left over. So 5 has a methyl coming out of it. So get that. Then to figure out where the cation goes, a lot of people mistakenly put it on 5 because it looks like the most stable position. But again, let's think about it. 3 lost a bond to 4, but it formed a bond with 5. So 3, gave away its bond to 4, but it gained one with 5. So 3 didn't lose anything really. 3 just moved its bond over. The person who really lost out in this deal is 4, because 4 lost a bond of 3, but nothing was ever made of it, right? Nothing was ever given back to 4. So the cation shifts from 5 to 4. Okay, so if you have to watch it a couple times and kind of work through the logic, I think if you just draw this a couple times, you kind of start to see how to do it. The pattern is always the same, but 4 is going to have the cation here. If we're doing a dehydration, right, it really doesn't matter anyways, because we can always take the proton off of 5 and form the alkene, which is great. And what we get is this here. Cool. All right, so that's about it. A lot of this was a review mainly of alkenes, but I think maybe quite a bit big information. A lot of the information in this was probably new. Sorry, that's an oxymoron. I think I just made conflicting statements. A good amount of this hopefully was review, but maybe some of it was also new to you guys. So definitely take the time to, go through the information that's important. Just do a quick overview of what I think was important. Really, this slide here is like, it's old information, not too important that you understand it. Maybe just understanding, how the pi bond, structure looks, or like the orbital structure looks like that. Of this page here, try to only understand this idea here of how anions, cations, and radicals sort of, where are they stable, whether it's on an alkane or an alkene. It's not totally important you understand everything here. Most of this will be revisited anyways later on down the line. Oh, I forgot to put something here. This will not work. This won't work. Clearly it won't work, right? It's too much energy. Here, again, this was a lot of food for thought. What I would really just understand is that substituents can have effects. And these are really the most like prominent examples of those two effects. So if you unfortunately have to memorize, and you can memorize these two, it's okay. Although I think understanding broadly the concept here is important. This is like a high yield question. It's at least one question that kind of tests you on this ability of knowing what is stable. One thing I'll add here is that stable doesn't necessarily mean non-reactive. It's a really weird thing, but if these hybrid conjugated forces are donating electrons to the pi bond, that means those pi bonds are high in electron density. They're actually nucleophilic. So we'll actually see that what we consider stable alkenes are actually the most nucleophilic alkenes as well, and the most likely to participate. There's just a few examples where that's not the case, and we'll go over those. So really understand this slide here. The elimination stuff, again, hopefully most of this was review, but I imagine probably this stuff here, especially if you're in the series class, is going to be completely new, just because, she didn't emphasize anti-periplanar state too much. I know Levens did a little bit. She emphasized it quite a bit. So that is something that, you hopefully remember and understand. But if not, that's okay, because, that's what we spent that whole hour on, was on this stuff. So again, understanding CH3 gives you a terminal alkene, right? You always get a terminal from this. You'll always get anti-syn from a CH2. So CH3 gives you terminal, CH2 gives you anti-syn. And then CH will give you E or Z. So it's E or Z. It's not E and Z. Let me make this very clear. It is E or Z. So it's very stereospecific, whereas this is stereoselective because you get both, right? According to, depending on your professor, they might only even want you to just draw the anti, because this is the major product. 7327, clearly this is major. And then just, all the different ways we proved that. The rule, again, so many people have tricks for these, so maybe my trick works, maybe it doesn't. Rotation is the best thing overall. If you can learn to rotate, you never have to worry because rotation will always give you the right answer. So I would only rely on the rule if you're low on time, right? Cool. Regioselectivity, again, only exists if there are two different beta carbons. That really matters for the rings, so understand that. Otherwise, if there's only one beta carbon that can react, right, then it's not really regioselective. If two can potentially react, then it's regioselective, and we can think about small or large. Again, really important for the ring examples here, okay? That just leaves us with the beta eliminations, E1. Not very difficult these, because in reality, right, we don't really do E1s with bromides if we had to, because E2 is just way better. I guess you could do an E1, but it's like, not really. Alcohols are really what we use E1 for, because that's the only way that we can make alkenes from them, right? They will just, and we only ever get the stable alkene from them, so it's something to look out for. And then just keep in mind the rearrangement ability of these alkenes. Cool. So yeah, that is going to be it. I will actually, I'll leave one more thing. I'm not going to solve this here because I don't need to, but there is one problem now that you guys can solve. And I know this is going to look crazy. I mean, that's kind of the point, is for it to look crazy. Shoot, sorry, hold up. I have to kind of forgot what it looked like. I have to go look at what this looks like again. If this is too hard of a problem you feel, then you can always revisit it after looking at the alkene reactions video. That one will serve as a better basis anyways. Let me just try to find this one. It's gonna be crazy if I add another 5 minutes to this because I can't find this problem. Okay, it's found it. So I did get that part right. Let's do this. Yeah, this actually might be a little, difficult, but it's okay. I believe in you guys. There's two ways to actually do this problem. I think maybe, okay, you know what? I will leave this for the next one, but I will put it on the screen anyways. I was trying to modify it, but it's not gonna work out. This problem, hopefully you should be able to do. You can take a crack at it now. You should be able to solve it somewhat based on information that I've given you. You can use a lot of things to help you solve this. This is really going to be more solvable after the alkene video though, alkene reaction. So I'll just leave it on the screen now. This is a great problem. Try it out. Maybe difficult on purpose if it feels difficult. Cool. All right. See you guys in the next one. See ya.